sir, you can share.
Okay, let me see how to share. Where is the sharing of screen?
So there is a present now option.
Yeah, present now. Can I? Okay. Okay. A window, your entire screen. A window. A Chrome tab. Okay. I would like the Chrome tab. Let me see. No, it's not. Cancel. So I wanted to use my iPad, which I usually do in Zoom, but somehow it's not letting me do that.
Yes,
I
sir.
guess I can only share my computer screen. I'm not able to um, not able to share my iPad where I could have done some annotations, but that's fine. Can you see my screen?
Yes,
Yes,
sir.
sir.
Yes, sir. It is visible.
Okay, all right. So we still have 7 minutes, so we'll
Yes,
just
sir.
wait for the
Yes, sir.
time. Yeah.
Yes, sir.
Okay.
Yes,
Yes,
sir.
sir.
So somehow, yeah, I'm unable to share my iPad screen. That would have been better because then I could have annotated, but that's all right.
Sir, if you have Google Meet application, then I think you can do it from your iPad.
I don't have Google Meet. Okay. Oh, I see. I see. Install Google Meet on my iPad itself. No,
Yes,
that's a good
yes,
Yes,
idea. So let me try. Okay. I don't have Google Meet. All right. In which case, I'll join the meeting from the iPad. You are saying. I see.
yes, yes, sir.
I don't know. It's taking time. I've installed, but it is not doing. I mean, oh yeah, now it's doing something. Yep. Now, okay.
Sir, I think you need to unmute yourself.
Okay. So, can you see my screen?
Yes, sir.
Okay, that's good. All right. So I think we can start. No, 2 more minutes. Let's wait until.
Yes, sir.
Okay, so good morning, all. It is a great pleasure for me to introduce our speaker for this session, Dr. Parthasarathi Roop. Uh, uh, Dr. Parthasarathi Roop is a professor in the Department of Electrical, Computer and Software Engineering at University of Auckland, New Zealand. He received his PhD degree in Computer Science and Engineering from the University of New South Wales, Sydney, Australia, MTech from IIT Kharagpur, and B from College of Engineering, Gindi, Madras.
Lalatendu,
Yes,
can
sir.
I stop you there? I will do my intro. It's not essential.
Okay, sir.
Thank you.
Okay, sir.
Thank you
Then
very
it's
much.
fine.
Thank you. Thank you very much.
Okay, sir.
Yeah. So I think it's just about 1 minute to go. I will start exactly at the hour. How many people are attending?
Sir, till now, 50, around 50.
Okay. So what would you like me to do? What would be the format? So I've got, so this is a series of, so I run a workshop. So I have a Spark project jointly with a colleague, Srinivas Pinisati from IIT Bhubaneswar, where this January we ran this workshop, which was a Spark workshop on formal methods for safe and secure medical devices. So I wanted to just mainly think that this is very relevant for this TQIP or something program where you wanted to introduce formal methods.
Yes, sir.
Now, as Lalatendu said, my name is Partha Roop. So I teach computer engineering in the University of Auckland, at the University of Auckland. And my research interests are in cyber physical systems. So I also lead a research group which is called bioemulation. And as I present today, you will get a kind of a view of what we do in bioemulation. So you can stop me at any time. You can ask me questions, or you can put your questions in chat, and Lalatendu can request me, and I will pause and I will respond to your questions. So I have two prepared lectures, and in the first lecture, we will look at how we can use formal methods for designing safer medical devices. So I will focus primarily on safety, and that's the first lecture. And in the second lecture, I will talk about security.
So I'll try and cover safety and security of medical devices from the point of view of the work that we are doing at Auckland. So basically, I'm sorry, I think I'm using the second presentation first. So let me see. Uh, Let me go to the previous lecture. Yeah. I will start off with the presentation where we'll talk about safety, and in the second one, we will look at security. So, how it all started. So, as I said, I'm a computer engineer, and I did not have much background in biomedical engineering, but around 2013, one of my colleagues, Professor Bryony James, she introduced this concept of ideas workshop. And during these ideas workshops, so people of different disciplines that tend to meet. For example, I met Professor Martin Nash, who is a researcher at Auckland Bioengineering Institute, ABI. And then he introduced me to now my collaborator and colleague, Dr. Mark True. And that's how we applied for funding, and a project called Heart on FPGA started around 2014. So that's when we started to work on kind of how can we apply computer engineering principles, particularly formal methods, to look at safety of medical devices. At that time, we were not so much looking at security. But this is not, our work is not unique by any means. There are quite a few projects globally. For example, there are EU-funded projects led by Professor Marta Kowalska from Oxford University. And there is a large NSF-funded project called Cybercardia in USA, which is primarily led by Scott Smolka at Stony Brook University. So these are two large global projects as well, which are looking at similar things to what we are doing. And the links are given. I will share my slides with Lalatendu later on. So this is the link to our website, and Cybercardia, as I said, as a Can people please mute if they are not speaking? Yeah. Can you hear me? Lalatendu, can you hear me?
Yes, sir. It's audible,
Okay.
sir.
Okay. Yeah. So just request colleagues to mute when they're not going to ask any questions. And this is the link to the work of Marta at Oxford University. So in general, as I said, my research is in the area of cyber physical systems. So what exactly is cyber physical systems? I mean, these are systems which can be kind of systems where you can have autonomous vehicles in the automotive area or robotics. Today we are going to cover medical devices, but also in the energy area, smart power grids. The key distinguishing feature of these CPS or cyber physical systems, unlike conventional computers, is that here many embedded computers are used to control physical processes. So let's look at, say, for example, an automotive example. And in the automotive example, basically, if you look at an autonomous vehicle, then you have the adaptive cruise controller. And the role of the adaptive cruise controller is to look at the speed of the vehicle ahead and accordingly adjust its speed. So essentially, the controller is controlling the kinematics of the vehicle based on the physical parameters it is sensing using the sensors. And it is not just one single controller. In an automotive example, there are many embedded controllers which are distributed using engine control units. For example, in an automotive application, again, you might have many CNNs which are doing things like traffic sign detection, pedestrian detection, which are executing on one engine control unit, and another engine control unit, a separate one, is kind of doing car following, meaning that it is maintaining safe distance from the car ahead. And these tasks are also interacting. They are also communicating. So this is a typical example where physical processes, in this case, the kinematics of the vehicle, the kinematics of the vehicle is controlled by embedded controllers. And these embedded controllers are usually distributed. But today we are going to focus on medical devices, which is kind of an instance of, again, cyber physical systems. So why are we looking at medical devices? The reason being that basically there are many medical devices. If we just look at pacemakers, about which we will study today, there are excess of 10 million pacemakers being used globally. But there is a reference here, which is again a researcher who is part of Cybercardia, Rahul Mangaram, and Rahul's group have done quite a bit of have done substantial work on this topic, and there they say that, and we also have found this, is that many of the pacemakers have been recalled due to safety issues. And much of the time, over 41% of these recalls are due to firmware issues. So this is something that we need to look at carefully. So, so this kind of device problems, if you want to go into more details, there is a very nice 2013 survey paper here I'm citing, which sort of talks about this problem in a little more detail. So basically here on figure A, on the y-axis is the number of recalls, and this is the year on the x-axis. And this study essentially is a 2013 paper and summarizes until 2011, so between 2006 and 2011. Now you will notice that number of recalls which are happening, which are computer related, is on an increasing trend, right? So this is increasing, and also total number of recalls is also an increasing trend. Now here again, if you look at figure B, this is a very interesting one, where the y-axis is number of adverse events in thousands. So and these are adverse events in thousands, and if you see here on the x-axis again, you see that these adverse events, which can include injury as well as death, is on an increasing trend. And you can see that the number of deaths is also significantly high. That there can be computer related, software related adverse events, and these can be substantial number in the thousands, which happened between 2006 to 2011. So this is a paper which is worth looking at. Now, whereas this paper talks about adverse events of all kinds of medical devices, right? So it looks at medical devices such as insulin pumps, automated insulin pumps, like cardiovascular defibrillators, which are used when a heart, in the event of a complete heart failure, to kickstart the heart, right? By generating electrical shock waves. But what we will concentrate on in this lecture is particularly on pacemakers. So these are a special type of device, and a pacemaker is a kind of you can think of it as a cyber physical system, where the pacemaker is the controller and the heart is the plant. And the role of the pacemaker is to control the heart such that the heart is not going into a condition which is known as bradycardia. Bradycardia happens when the heart is beating less than 50 beats a minute. So if the heart beats less than 50 beats per minute, then the heart has bradycardia, and a pacemaker is a device which monitors the heart and then paces the heart in the event of bradycardia. So how does it do it? Here we'll look at a particular pacemaker, which is a DDD mode pacemaker. And in the DDD mode pacemaker, it's a dual chamber where both chambers are sensed and paced. So here we are essentially, we have got two leads going into the heart, one into the right atrium, which is sensed by this signal. You can think of it as a kind of an input, which after signal processing will become a Boolean input, which is true when the atrium produces a beat. And likewise, VS is a ventricular sense event, which is true when the ventricle produces a beat. And if the pacemaker notices that these beats are not produced as per some standard timing intervals, which are predefined intervals, then the pacemaker will output either a pace into the atrium or a pace into the ventricles. So that essentially, in a nutshell, is an example of a cyber-physical system where the physics is the dynamics of the heart, about which we will look at in this lecture. And the pacemaker is a kind of a controller, and its safety aspect we'll look at in the next lecture. Basically, now the pacemaker's role is to ensure timing properties between these kind of signals that it is sensing. And when these timing properties are not satisfied, pacemaker kicks into actions. Now, there have been both safety issues, but there have been security issues. For example, in a 2017 FDA report, 465,000 pacemakers were shown to be vulnerable to hacking. And hackers could, for example, induce arrhythmia. So pacemaker paces the heart only in the case of bradycardia, where the heart is beating slowly, but hackers could induce kind of tachycardia, where they could pace the heart so rapidly that the patient could die, or they could drain the battery, for example. So we will look at this aspect of heart pacemaker as a CPS in some more detail. Now, first we will look at, I'm not sure if I have YouTube installed. Maybe this will not work. Okay, I will show this video on my computer. So this is a demo of an emulation environment we have created, and I will show that to you towards the end of this lecture. We'll come back to this demo. So what we have tried to do is to use computer engineering principles to this particular problem that I pointed out, which is that pacemakers, which are meant to save lives, can also fail. So how do we prevent such failures? So essentially now that brings me to the topic of this lecture, which is formal methods. So I'll start off with some definitions. So formal methods are a class of techniques which are mathematically founded, which were developed for software and hardware systems. So initially for hardware, and then subsequently for software. So initially, for example, there is the technique called model checking, which became very, very popular for verification of hardware systems, but subsequently it has been also applied extensively for verification of software. Now in formal methods, mathematical rigor enables that users can analyze the system statically. That means without actually executing your hardware or software, you can perform static analysis to determine, for example, the worst case execution time of some tasks. So this is possibly Lolatendu worked on mixed criticality systems. So that's the kind of static analysis you can do. Or you can perform some kind of static verification to verify some properties of systems. And formal methods have been used widely, and some of the key contributors have received some of the most outstanding awards in computing. So the techniques encompass those founded in mathematical logics, process algebras, programming languages and semantics, and automated techniques of proof. And these are just a handful of techniques I'm pointing out. There are many more techniques, such as those founded on set theory, like the B method and the B toolkit. But the significance of formal methods and the contributions of formal methods can be sort of attributed to the success of formal method researchers. For example, if you look at people who have made contributions to formal methods, and here is just a snapshot, this is not all the people, but for example, Tony Hoare, 1980, received a kind of Turing Award for the process algebra CSP. And likewise, Robin Miller for calculus of communicating systems. Amir Pinueli, who introduced the concept of temporal logics, which already existed in philosophy, but he showed that using temporal logics, we can essentially reason over programs, particularly reason over reactive systems. So to reason over reactive systems. Amir Pinueli showed the link between temporal logics and reactive systems. Subsequently, these three gentlemen, they invented model checking, and they received the Turing Award around 2007. Clark, Emerson, and Sifakis, they independently invented this kind of proof technique, which is a very interesting proof technique where you actually don't do proofs like we typically do. For example, in high school, we learn about Euclidean geometry, and we learn to do proofs using different theorems we have learned to prove new theorems, for example. But those proofs are much more manual. In fact, there are techniques which you can do in a similar manner for software or hardware, known as theorem proving. But model checking is a purely mechanical method of proof. So it's like many people can use model checking without having in-depth understanding of formal methods or how these proofs are done. So, and techniques of model checking have become kind of industry standard, with model checkers being used widely. For example, many commercial tools have model checking support. For example, SCADE, for example, which is used in the aviation sector, or MATLAB Simulink state flow. All these have model checking support. And more recently, in 2013, Leslie Lamport received kind of formal methods for real-time systems. His work on temporal logic of actions, and actually Lamport was one of the first persons who created kind of definitions of safety and liveness, who distinguished between safety and liveness. Any questions until this time? Maybe I will pause for a minute or so. Anybody has any questions?
No, sir, no questions.
Okay. So please pause me, and from time to time, I'm citing some kind of references. For example, here there is a very nice survey called Formal Methods, Practice and ACM. Practice and Experience, which appeared in ACM Computing Surveys 2009. It's a little bit dated, but still it's a nice survey. So now what I want to show is our proposal for device validation. So how will we validate the device? So essentially, I will show you some videos where typically what they do when they validate a device is you can do simulation. So simulation, as you know, is provide input stimulation. This is an open loop system, and you observe the outputs. So you have a pacemaker, you keep on providing input stimuli, AS, VS, AS, VS, and observe what the or AS, VS, AP, VP, those four signals that we looked at, and then observe how the pacemaker is responding. So you provide AS/VS and see AP/VP. And this is an open loop kind of system. But actually, how typically engineers verify or validate, rather, not verify, they validate. So I will distinguish between validation and verification. So validation is essentially testing. And testing can be done either open loop or closed loop. So simulation is essentially open loop testing, but you can also do emulation, or this is sometimes also known as hardware in the loop in the automotive domain. So what's hardware in the loop? In hardware in the loop, essentially you have the engine control unit and you connect it to so that is so you have a kind of a model of the a kind of a real-time model, and then you connect that to the actual plant. So for example, what typically in the pacemaker context, what they do, and I'll show you a video later on, where they will connect the pacemaker to an animal's heart. So the pacemaker's timing can be configured. What they will do is they will implant a pacemaker in a, for example, in a sheep heart. They will specify the timing intervals appropriately, and then they will see if the pacemaker is sensing and pacing correctly or not. What they can also do is they can induce some disease states in the heart. For example, in our lab in the medical school, they will induce some kind of heart failure, or they will cause some kind of arrhythmia in the heart and test if the pacemaker is pacing correctly. Now, these two are fine. The limitations of these is that these systems are so complex that exhaustive simulation is not possible. The reason is that the input-output space is if not infinite, is close to infinite. It's actually infinite because this is a real-time system, which we will see shortly. Now, emulation, if you want to induce arrhythmia in a sheep's heart, you can only do it for a short interval of time, say 4 hours, 5 hours, until which you can keep the sheep alive and you can do the experiment. Now, these two have limitations, and even though you can do these, still pacemakers are being recalled. So we have a paper in one of the IEEE journals where we have looked at an approach called remulation or reverse emulation, why it's reverse emulation is that basically you take an actual pacemaker. So in emulation, you have the actual heart and you connect it to a model of the pacemaker or a pacemaker. So this is hardware in the loop or organ in the loop. Sometimes this is also known as organ in the loop. But what we want to do is, so typically this is the controller and this is the actual plant. Now, in our case, we call it reverse emulation. The reason is basically the plant controller relationship is kind of reversed because this becomes kind of the pacemaker is a black box system, and we want to design a heart that can be connected to this pacemaker. So for the heart, this is kind of like the plant, if you think. So we are now actually synthesizing the plant and synthesizing it to make it like an artificial organ. So this is what we call as a heart on a chip, or HOC. And I will show you a video of the HOC that we have designed and this approach that I'm going to present in this lecture. So our approach is actually inspired by what's happening in aviation. In aviation, there is a tool called SCADE, which is developed by a company called Astral Technologies. And this is inspired by an approach called synchronous programming. And in synchronous programming, what happens is that the concurrency of the control system is sort of made into a kind of a synchronous program or a synchronous paradigm, such that it is easier to validate this concurrency and perform static analysis. And the SCADE is a very nice tool chain. Because of the synchronous semantics, SCADE is the only compiler in the world that I at least know of that generates automatically certifiable code that is compliant with this standard. So our idea, we were familiar with SCADE. So our idea was, can we do something similar to what they have done in aviation, where in aviation, you know, failures are very, very expensive. We cannot tolerate any failures because that kills a lot of people. So software certification is sort of very rigorously done by tool chains. So our idea, could we do something similar in medical devices? For example, Airbus A380 is designed using SCADE, and actually SCADE's approach is founded on formal methods. Now, in the medicine domain, there is a very interesting book, which is by this gentleman called Atul Gawande from, I think he's from Johns Hopkins, I'm forgetting. But anyway, or Harvard Medical School, one of them. But what he found is that many mistakes, many problems in medicine happened because during surgeries, many deaths happened. For example, some particular medication was given as an overdose, or there were some steps which were done in a reverse order. So what he proposed is an idea called the checklist manifesto, which is now adopted globally and is a kind of an standard which is adopted by all hospitals. It's kind of WHO acknowledged checklist manifesto as something that should be followed. And there Atul is talking about simple checklists as a means of kind of ensuring that failures are not happening. But there are many other people who are also, I mean, beyond checklists, people are actually thinking of how can we use computational principles to avoid kind of accidents in medicine. There is a gentleman who is a doctor with whom I have some links. His name is Steven Belknap. And Steven has a programming language which is called POP-PL, which appeared in ACM Transactions on Programming Languages. Steven is a medical doctor, is not an engineer by any means, but POP-PL is a proper programming language which goes beyond checklists into actual. So checklist is just a sequence of steps. That's it. So you maintain a sequence of steps, and that has been shown to avoid many, many drastic things. But Steven goes a lot further, and in his work, he shows that basically opioid prescriptions, there are many failures with opioid prescriptions, and POP-PL is a programming language, is a full-blown programming language for the safety analysis of prescriptions of medicines which can cause harm. And our ideas are sort of inspired by some of these ideas. So now, with that introduction, I think I've spoken for nearly 30 minutes. I would like to give you a kind of a 5 minutes break just to reflect on what we just now learned. Or I mean, I just gave an overview. I have not actually, I just introduced the problem. I have not talked about the solution at all. But I would like some interaction. So let me start my camera and maybe you can ask me some questions. And then I will go into more details. So anybody at this stage can ask me any questions, or you want any elaborations, anything like that.
So that skate tool is a freeware or it is?
No, it is a commercial tool. Unfortunately, it's not a freeware. I mean, it's like MATLAB Simulink State Flow, right? So Simulink State Flow is not a freeware, and likewise, Skate is not a freeware. But if you are interested in synchronous programming, there is a environment which is called Keeler, K-I-E-L-E-R, which is a freeware, which is maybe I can later on give an introduction to Keeler also. I'll show you. I'll show you a pacemaker in Keeler. Okay. Yeah.
Thank you, sir. So I think, sir, Jhalak Hota wants to ask something.
Sure. So who are the people attending? Like,
good morning, sir.
Yeah, hello.
Sir, good morning, sir. I am Jhalak. I want to know a little bit about temporal logic. I mean, what is that? I never heard of it.
Okay. Well, today I'm not introducing temporal logic, but I could talk about temporal logic a little bit. Yes, sure. Thanks for asking. Yeah, sure. I could talk a little bit about temporal logics. Sure. So what's the background of the people who are attending?
Sir, some of them are students, means undergraduate students.
Okay.
And we have 5 to 10 PhD students, and maybe some assistant professors from various universities.
I see. So who are attending this course, is it?
Yes, sir.
Yes, sir.
Okay. Good. So there was a question about temporal logics. Shall I talk a little bit about temporal logics? Shall I digress from the topic and talk about temporal logics? Let me continue a little bit more. Let me introduce the topic, and then I will come back to temporal logics. Yes.
Okay, sir. Okay.
Sure, sir.
Anything else?
So, participants, if you have any question, you can ask.
Yeah, anybody can ask anything. I mean, no point in just, I mean, the problem with this kind of Zoom-based sessions is you don't know if people are following or not, or Zoom
Yes,
or, Google Meet, whatever. Okay, so I'll again go and share my screen.
Yes, sir.
So is it, can you see my screen yet?
Yes, sir. It's visible. Yes.
So I'll come back to that question of temporal logics. I'll give you a brief introduction to temporal logics, no problem. So let's look at first a model which is known as a hybrid automata. I will also give so I'll switch back to my computer where I've got some Python-based animation of hybrid automata, which I will show on my computer. And I will also show the SC charts because you asked Lolatendo about whether SCADE is open source. No, SCADE is not, but I'll show you an open source software, which uses similar principles. Okay.
Okay.
All right. So now, basically, what I'm going to talk about next is let me skip this. So I was talking about this concept called emulation, right? So what is emulation? Emulation is an approach by which we will create kind of an artificial heart, and we'll connect this to the actual pacemaker. So this is an actual pacemaker. It can be a Medtronic pacemaker. It can be any pacemaker, as long as we know the standard interface, then we can connect the heart to the pacemaker. Now this heart, of course, the heart is as you know, is a biological pump. So basically heart has, maybe when I go back to my computer, I will again join after this hour through my computer, and I will show you some stuff through my computer, which is not available in my iPad. So basically, the heart is a pump, and it has, as you know, it has two cycles, the systole and the diastole. So the systole is when the heart is squeezing to pump out the blood, and diastole is when the heart muscles are relaxing. That's why the heart is beating rhythmically. A standard heart, which is a normal heart, beats 50 to 120 beats per minute. Now, of course, the heart being a pump, there are a lot of things. The heart is actually connected to our central nervous system, and particularly a nerve which is known as the vagus nerve, which is synchronizing our breathing with the heart. That is something I'm not at all going to talk in this lecture. So actually the lungs and the heart are coordinated also with the brain, which is coordinating, our hormonal activity. For example, you might have noticed that if you are too nervous, the heart is beating, exam time, or for example, someone is very anxious about their relatives, then the heartbeats changes, because these are because of brain activity, because of hormonal activity. So this is a very, very complex organ to emulate. I'm not saying that we'll emulate everything, but using formal methods, we'll emulate what is known as the electrical conduction system of the heart. The electrical conduction system essentially consists of kind of many cells on the heart, which we will call groups of cells, are known as nodes. For example, one node is known as the sinoatrial node. This is the normal pacemaker of the heart, and this generates, this is an autoarrhythmic cell, meaning that an autoarrhythmic cell is a cell which automatically generates electrical activity. And as the electrical activity is generated, that electrical activity propagates to its neighbors using these things which we call as paths. So what you have is nodes. So the nodes are, the red nodes are called pacemaker cells. So anything shown in red are kind of cells which are pacemaker cells, meaning that they beat automatically, rhythmically. The main pacemaker is the sinoatrial node, but sometimes due to cardiac disease, this node might fail. So when it fails, then other nodes which are autoarrhythmic can take over that activity, because this is a kind of fault tolerant system, if you like. Even though there is some fault, still there are other nodes which can take over. Now, the other kinds of blue cells are what are known as cardiac myocyte, or the muscle cells. These cells cannot trigger automatically, but they require the electrical activity of their neighbors to stimulate. And the third type of cells are these orange cells, which are known as subsidiary cells. Subsidiary cells are cells which are a combination of pacemaking and cardiac myocyte, so they are hybrid. So what we have done is we have created kind of a abstract cardiac model by identifying key groups of cells and connecting them through paths, where paths model the delay or the time taken for conduction to happen from this cell to this cell. So path model the timing, conduction can happen in both direction. This cell can communicate with this cell can communicate with this cell. So when this stimulates, that voltage propagates after some delay here, and so on and so forth. So these are bidirectional paths. Now we have got, so what we are doing in our emulation system is we are not emulating the pumping activity of the heart or the hormonal response of the heart. We are only emulating the electrical conduction because that is what the pacemaker is sensing. The pacemaker is only sensing this electrical activity through two leads which are inserted inside the right atrium and the right ventricle. So that's what I will focus on. Now let's look at the model of a cell. So how can we formally model a cell? Now this type of model is what is known as a hybrid automata. So what exactly is a hybrid automaton? In hybrid automaton, so unlike all of you know about finite automata or finite state machines, so in finite state machines, you can only model systems which are finite state. But here, what we are modeling is the electrical activity of a cell. So a cell, this is what is known as the action potential of a cell. So typical, and this is a cardiac myocyte. And this is a model we developed here at Auckland. So this is a cardiac myocyte model developed by my group. And essentially, this is kind of the action potential which is generated by executing this this cell model, which looks like a finite state machine here. So you can think of this as 4 states, Q0, Q1, Q2, Q3, which is something like the cell is initially resting, but if you provide a voltage which is greater than this threshold voltage called Vt, then the cell will be stimulated. So, so from resting, if you give it a voltage, if you stimulate it with a threshold voltage which is greater than Vt, it will get stimulated. Then the voltage will steadily rise until it reaches some maximum value V0. And after reaching that value, automatically the cell will go into a kind of a refractory phase. This is known as effective refractory, ERP. So initially resting, then stimulated. So from resting, you go into stimulated, then you go into upstroke. So that's the upstroke phase. And then this phase is the effective refractory phase. And then the final phase is relative refractory phase. So that's that phase. Now, each of these can be modeled sort of like a state, Q0, Q1, Q2, Q3. Q0 essentially covers resting and stimulated, and then Q1 is upstroke, then ERP and RRP, and then again we go back to Q0. So we become resting again. So now this is not a finite automata, but this is what is known as a hybrid automata, because this is an infinite state system, because essentially what this is doing is that it is modeling the voltage of a cell. How is it doing that? So let's look at the location Q0. So what we do to model the voltage of a cell is basically we have got some ordinary differential equations, which are used for specifying the rate of change of some real valued variables, right? So Vx dot, Vy dot, and Vz dot are 3 components of the voltage of a cell, where the rate of change of Vx dot is C1 times Vx, and so on and so forth. And then we have an algebraic equation which specifies the voltage V as Vx which specifies the voltage V as an algebraic equation Vx minus Vy plus Vz. Now, so So basically, this is kind of a model where we combine ODs with uh, discrete mode switches of SSN. So, we combine these two. Now, basically what you will notice is that every location has an invariant. Every location has an invariant. An invariant specifies a condition which when it is holding, you can remain in the location as long as the invariant is true. For example, as long as the voltage is less than Vt, and G of V is the summation of the voltage of the neighbors. As long as G of V, the summation of the voltage of its neighbor is also less than Vt, then this is my invariant. As long as this condition holds, then only I can remain in this. Q0 is not a state because this is an infinite state system. This is known as a location or mode. So I can remain in Q0 as long as basically this invariant condition holds. However, if a guard condition holds, when G of V is greater than Vt, then I can make a mode switch, and I must make this mode switch prior to the invariant becoming false. Invariant should never become false. Invariant should hold forever. So basically what's happening in the execution is we start the execution, we are in Q0, the rate of change of the voltages are specified as ODEs, and the voltage is a continuously changing phenomena which is changing based on this algebraic equation where the three parameters are controlled by three ordinary differential equations, and before the invariant becomes false, when G of V becomes greater than Vt, we make a mode switch, we go to the next location, and similarly we remain in the next location as long as the invariant holds. So we can model individual cells, and then basically these models are reasonably complex. The model, and there are many model parameters, like for example parameters like theta, C1, C2, C3. All these are sort of we have done experiments and we have identified those parameter values such that not only we can mimic this kind of action potential faithfully, like published action potentials, but also we can mimic the dynamic behavior. So these cells are not static. For example, we talked about two refractory periods. One is this phase, which is phase 2, where if you provide stimulus, the cell will simply ignore such stimuli. The cell ignores such stimuli, the reason being that the cell is an effective refractory. Whereas in relative refractory, during this phase, if you stimulate, then the cell will produce action potentials, right? So this is like an inertia phase where the heart is still recovering, the cell is still in recovery mode, because these electrical phenomena that we see are actually due to some chemical processes. There are three channels: sodium, potassium, and calcium, and these three channels are basically are leading to this kind of electrical activity. And the cell, when you stimulate it, these channels open and then they close, and so on and so forth. This is known as depolarization and repolarization respectively. And during phase 2, the cell is still recovering, so if you stimulate, it will not get stimulated. But during phase 3, if you stimulate, it will stimulate again. But you will notice this in this timing diagram, where this is the x-axis is the time in milliseconds. So this is my first action potential from 0 to 160. But if I stimulate here, which is in the ERP phase, and as I stimulate early into the RRP phase, you will notice that the action potential durations are shorter and the maximum voltage VO is less. But as the cell gets more rested, the action potential durations increase. The next excitation, it increases further, and finally you see that it becomes like normal excitation again. So this kind of dynamic behavior is very, very important. Now, how do we know that our cell model is working correctly? So what we have done is we have compared our model, which is a mathematical model, with models which have been published based on actual experiments of these cells done by biomedical engineers. So here is the action potential. The dotted line is parameterized hybrid automata model that I presented, and the blue line is the 10 Tusser model, which is kind of a reference model, very well-known model. And you'll notice that our model sort of mimics very closely. The correlation is quite strong with actual action potentials of cardiac cells, cardiac myocytes. And how do we know that we are actually exhibiting dynamic behavior properly? Now, I showed in the previous diagram is that the duration of the action potential changes as you excite at different times. And this is what is known as the diastolic interval. As you increase the diastolic interval, what happens is that the action potential duration increases steadily and then plateaus. And that is what we observed in this diagram. And if we plot the action potential duration by increasing the diastolic interval, we also see that compared to the 10 Tusser model, our parametric model also performs very, very closely. So in essence, we have a mathematical model which closely follows reality. So then essentially next we can also formally model the path which models the conduction delay. This is modeled using timed automata, but I think I will give a break at this stage and I will give a 5 minutes break and we can resume. And next what I will do is I will join on my computer and I can show you some stuff there. But first, after the break, I will introduce a little bit about temporal logics because one of you asked about temporal logics.
Okay, sir.
So I will give a short 5 minutes break.
Okay, sir. No problem. Thank you, sir.
And then we will resume after 5 minutes. People can go for a short drink. I will grab a drink and then we'll resume after that. Is that okay? Any questions? So any questions? So far, what I have presented, because I thought it's more like a research seminar, so I presented more about a gap in research and what we have done. But I see that the audience is very diverse. So in the second hour, instead of presenting more research stuff, I will just show you some more fundamental stuff. I will show you about temporal logics, a little bit about temporal logic model checking. I will show you some tools for verifying these kind of systems, and I will show you some videos instead of just presenting more, this kind of research-oriented stuff. So what I have presented is a gap that medical devices are typically tested by testing them on live animals. What I am presenting is a methodology by which we can design a heart on a chip by formally modeling the heart as a composition of many cells and paths. And then from this, we can automatically generate hardware and software. And then we can use this to test pacemakers. Our compiler is correct by construction like the Cascade compiler, so that the generated code is sort of certifiable. If we wanted to certify it, it will be easier to certify the generated code. So that's the kind of the story that I'm trying to tell you.
Okay, sir.
Sir, I have a question. Sir, can we model it in terms of mixed criticality systems? Is it possible?
Definitely. Definitely. This is, if I present you the model, you will see actually these are all mixed criticality systems in the sense that what I'm presenting is a hard real-time system.
Yes.
But you can mix this with some kind of soft real-time systems. So in general, this should be a mixed criticality system. In general, you can consider this as tasks of varying levels of criticality. But currently, it is just a hard real-time system.
Okay. That means all the tasks has same criticality level.
All tasks have same criticality level at the moment. But we could think of modeling this as a mixed criticality system. It is possible.
So Priyanka
Sir, I have a
Mitra,
question.
Sure.
So if we talk about simulators, so are they providing the accurate results as compared to mathematical model and emulators?
The correctness of simulation is an interesting question. So when you simulate, what do? You write a test case. Okay.
Yes.
And if the test case passes, you feel that the system is working correctly. Is that correct? Well, if a test case passes, you have only seen that that particular trace satisfies that condition. But that doesn't mean that the system is fully correct. Okay. So that is simulation. Now, to say that a simulator is good, then you have to do all different types of coverage criteria. You need to know how good your test cases are. So you have to write different kinds of unit tests, regression tests, acceptance tests. And then you have to have different kinds of coverage criteria to determine how good your test cases are. The coverage criteria might be MCDC coverage, where you are looking at, how many states have I covered? How many transitions have I covered? If you consider your system as a collection of state machines. But that is not rigorous enough. Okay. Whereas if we use mathematical models like what I presented just now, then we show that mathematical model's dynamics is very close to actual biological cardiac cells. And then if you emulate this behavior, then you can emulate for a long time and hopefully you can detect errors. This is still testing. This is not formal verification. We'll come to that. It's still testing. But you are testing for a long duration using an actual device in closed loop.
Okay.
okay. So do you
So
have
thank
any
you.
questions? Do you have any questions, participants?
Sir, I want.
Okay, Jhalak.
Sir, I want to you, sir, told about invariants. So basically about this invariant. So I want to know in terms of a behavior of a heart, how we could interpret invariant in that sense.
So an invariant is, for example, so invariant is just a condition. So what exactly is an invariant? An invariant is a condition which is kind of an upper bound of how long you can stay in a location. That's it. So from the point of view of the heart, how long you can stay maximum in the resting phase. You can stay as long as the aggregated voltage of the neighboring cells do not exceed the threshold voltage. So that's an invariant. I will give you a simpler example of a water tank heating system. All right. So invariant is simply a condition which is an upper bound. Invariant should never become false. Before an invariant becomes false, an egress transition and outgoing transition should become true, so that you can move from one location to the next.
Okay, sir. So thank you, sir. We will take 5 minutes break and then
Yeah, we'll take a 5 minutes break, and after that, I will show you some more stuff. Maybe not just my slides, but I'll show you a combination of things because so many of your undergraduate students are attending.
yes.
Okay, so maybe I will rejoin from my laptop next, but temporal logic, no. So no, I will remain here and then I will switch to my laptop because the SC chart tool chain and Uppal, these are two softwares that I can show you, which I can show you from my computer.
Sir, you may join from both the laptop as well as iPad.
Yeah, I could do that too. I will try. Even if I mute the devices, still there is an echo, but we'll see. We'll see. Let me try. Let me try. Okay.
Okay.
Cheers. Bye bye. So, are people still there? Can I resume?
Yes, sir.
Yes.
All right. So, so far, quick recap. We are modeling the heart using formal methods, where we can model individual cells in the heart, and we can model the timing of the voltage propagating between two cells using the concept of paths. So I presented here the concept of a hybrid automata, where an hybrid automata models any dynamical system using ODEs and kind of discrete mode switches. But timed automata is a subset of hybrid automata, where essentially you just model the timing delay. For example, what we could do is we could model two cells which are say the cell I and the cell J, and we can model the voltage propagation in either direction. So that could be modeled as a timed automaton. So what exactly is a timed automaton? A timed automaton is one where basically the only ODE so timed automata again has a collection of locations. For example, idle is a location, direction I is a location, direction J is a location. And this is a timed automata we have designed to model the timing delay of paths. So path from a cell I to cell J could be that the voltage is propagating either from I to J or from J to I. So in either direction. So that's why you can see this symmetry.
Sir, your screen is not visible.
Oh, my screen is not visible. Then you should tell me before. Okay, I'm sharing my screen. I don't know why it's not visible. Screen recording broadcast. I'm already broadcasting my screen. Okay, what shall I do? Shall I stop broadcasting? Start again. Oh, shared screen.
Present now, sir.
Screen broadcast. Start broadcast. Is it visible now?
Yes, sir.
Is it visible now?
Yes, sir. Yes.
Yes, sir.
Okay. Thank you. Thanks for letting me know. So we are talking about the timing of how the voltage propagates from a node I to node J. Okay. So where I and J are two hybrid automata, and in between two hybrid automata, to model this delay in timing of the voltage conduction, we can model these as what are known as paths. And paths are nothing but timed automata. So in timed automata also we have locations, but we have only a we do not model arbitrary ODEs. We only model clocks, where a clock X or any clock variable T, there is only, so if X is a clock, X is a clock X, there is an implicit ODE associated with it, which is X dot equal to 1, which mimics how time progresses uniformly. Now this is a clock which does not have any clock drift. If you want to model clock drift, timed automata can be also used to model clock drift. So now here we can use a timed automata basically to mimic this behavior where you will notice this kind of symmetry where either the cell I's propagation is happening in this direction, or cell J, so this is when direction I, or it's propagating in the other direction. So typically the cell is idle. Typically the cell is in idle state or idle location, and if the first cell's action potential goes to Q2, so you remember Q0, Q1, Q2, Q3, that means this is in the stimulated phase, and the second cell is not stimulated, then you set direction I. Otherwise, it is direction J. That means this cell is sending its voltage in this direction. And then what you do is, if direction I, then basically there are some conditions after which you, based on that condition, you go to this wait state where you wait as long as the value of the clock is less than some delta ij. Delta ij is the propagation delay along this path. So as long as that, so that means this cell is stimulated, you wait for delta ij time, and after delta ij time, simply you start to relay that voltage to this cell. So that's how, using timed automata, we can model kind of the delay in voltage propagation along the paths. So this is what is known as a path automaton. And here T is a clock variable. And I will show you some more examples of timed automata later on. So then what do we do? Then basically we have a compiler which automatically generates code. There was a question, why, what is the distinction between your approach and the approach of testing? Our compiler sort of uses mathematical semantics like SCADE when it generates code. I think I will skip all this because I don't know the background of the audience, but the basic idea of the compilation I will show you. So our code generation, so this is a paper we wrote long time ago in this conference called Design Automation and Test in Europe 2016, and there is a more recent paper in International Conference on Cyber Physical Systems 2020, where this compiler's results are published. In date, we wrote our first compiler, and here we generated purely software, that means C code. And in 2020, we can perform hardware software co-design, where we can generate VHDL as well as C. And but the basic principle is the same. Given a hybrid automata, we can transform a hybrid automaton into an FSM. So how do we do that? So essentially what could be done is, the idea is not that difficult. Now, if you follow the synchronous semantics, the synchronous approach, then in the synchronous approach, the concurrent system of FSMs execute using the notion of ticks, where each tick has a fixed time delta, which is the synchronous step. Then the same principle could be used as you solve the ODEs using, here I'm showing using forward Euler. So if I have an ODE, I mean, this is straightforward, even your students will follow. If I have an ODE which is in the cardiac cell, I had Vx dot, Vy dot, Vz dot. If Vx dot is C1 times Vx, then I can transform this using forward Euler and this synchronous step size delta, where Vx prime is Vx plus delta times C1 times Vx, right? This is very standard, where I can use this integration step size as the fixed step size delta. Then I can do this to transform hybrid automata into an FSM as follows. So as long as my invariant condition holds, then I remain in my location Q0 and keep on taking self transitions. This is what we have given as mathematical semantics to our hybrid automata. And in a hybrid automata, as long as an invariant holds, we take these transitions, which are known as intra-location transitions. That means I'm in the same location, Q0, and all I'm doing is I'm changing, I'm evolving my ODEs, and I can evolve my ODEs using forward Euler. So I can evolve ODEs using forward Euler by taking this delta step. So every tick, every delta step, I evolve my ODEs. I keep on doing this as long as this transition condition is not true. When this transition condition is true, I do the updates exactly as specified in the transition condition, go to the next location. So this is what is known as an interlocation transition. So this is intra-location. This is interlocation. And using this, I can convert an individual hybrid automata. And then because of synchronous execution, what we can do is basically what I can simply do is for all the automatons, I can run them in any random order. That's because what we do is a delayed synchronous semantics. That means what is delayed synchronous semantics? Whenever this automaton updates a variable that this automaton is reading, it always reads the value from the previous tick or pre. So when you use pre, it is well known, and there is a theorem using which we can show that if you order FSM1 to FSMN either truly concurrently as in hardware in parallel, or you execute them in an interleaved manner in any order, our semantics guarantees that the result produced is going to be identical. So we use that semantics. We use a simple cyclic executive where we execute the automaton in some fixed order, and then we update the outputs, then update the inputs for the next cycle. So this is essentially the idea. And we have a we have a new kind of programming-based abstraction for hybrid automata, which is known as HAML, which is Hybrid Automata Modeling Language, which is a human-readable form of hybrid automaton, from which if you have a collection of hybrid automata, then from this we can automatically generate our code. Our tool chain is open source, and you can get all the software freely available. We have recently used hybrid automata for modeling COVID-19. And we have modeled very faithfully same cyber-physical systems approach. And there is a paper I will show you where we have used HAML to model the progression of COVID-19 in New Zealand and as well in Italy. Our difference is that unlike existing models, which only model the physics, we model essentially the physics of how the dynamics of the disease as the plant, but we also model government actions as the controller. So we, for the first time, introduced cyber-physical systems approach to COVID-19, and there we have also used HAML. For people who are interested, I will show you a link to the paper, which is currently under review in Nature Scientific Reports, but it is openly available. Okay, so I think I will stop here, and I will now show some questions. Like I think because many students are there, I also wanted to talk a little more about our work on security, but I think I will pause here. I will rather show you some tools and some videos, some more interesting stuff. Is that okay?
Sure, sir.
Okay. So now temporal logic, someone was asking me temporal logic. Let me see if I can show you some concepts of temporal logics. Where can I find them? Maybe it's not available on my iPad. Oops. It is not available on my iPad. I will I will now join from the other device, and we will see that shortly. Give me a second.
Okay, sir.
Give me a second, or I will. So if I mute here.
Can you hear me? Lalatendu?
Yes, sir.
Okay.
Yes, sir.
Good, good, good. So let me quickly show you some stuff. The right lecture where I can talk about temporal logics. So, so first of all, okay, we can ignore all this. So I'll just talk about temporal logics. So, okay, let's talk about. Can you now see my screen?
Yes, sir. Yes.
Okay, good. So if we want to model the traffic light intersection between a traffic light which goes in north-south direction and one which goes in east-west direction, then the total state space, each light is red, yellow, or green. So the total state space is C cross C. And we can model this as a Moore style state machine where each state we indicate the light color in north-south direction followed by the east-west direction. Is that clear? Okay. So north-south is red, east-west is red, or north-south is red, east-west is green, and so on and so forth. So this kind of a mathematical model is known as a Kripke structure. And you will notice that there are totally 9 states from 0 to 8. Now, when we talk about logics, in particular temporal logics, there are 2 types of temporal logics. One which is known as LTL or linear temporal logic. The other one is known as branching time temporal logic. So why did this distinction? Now with linear temporal logic, so what exactly is temporal logic? Temporal logic is a logic for reasoning over time. Okay. So basically time is considered as a linearly ordered set, or time is considered to be kind of a tree structure where time has branches in the future. For example, if I look at my traffic light controller, then I can unroll this traffic light controller starting from the initial state, and I can consider several paths, right? There are many infinite paths, RR, RG, Ry, Rr, Rg, and so on and so forth. That is one path. A path is an infinite sequence of states. I can have another path. Linear temporal logic reasons over the sets of paths. So it takes a model, it considers the overall behavior as just a set of paths. That means these are just linear traces. A logic where you can reason over these linear traces is known as linear temporal logic. A logic where past is completely ordered, like for example, if I am in RR now, my past I have reached through this RR, RG, RY, RR. So that is totally linearly ordered, but my future is branching. In future, I can go to either GR or RG. So when past is totally ordered, but future is branching, that kind of logic which can express this kind of branching behavior in the future is known as computation tree logic. So how can we express properties in this logic? So, and what is the syntax and semantics of this logic? Now, what we can do is we can use some kind of temporal operators combined with some path quantifiers. So basically, computation tree logic expresses properties where past is totally ordered, but future could have branching. Now, what I will do is I'll join with my iPad and I will try and explain this logic with some annotations. So let me see if I can join also from my iPad. Let me mute this. And
Can you hear me?
Yes,
Hello?
sir. Yes, sir.
Okay, you're there. Okay, great. So I was presenting temporal logic. So I will again share my screen broadcast.
Yes, sir. It is visible.
Okay, great. So I will now. So we were talking about temporal logic. It will be a bit difficult to present from the. I airdropped it here, so I can now. So everybody followed what a Kripke model is. So it's just a finite state machine like model where states are labeled with what are known as atomic proposition or atomic formula. So let me first define what a Kripke structure is. A Kripke model, Kripke structure is nothing but a set of states, the transition relation, some initial state, and the labeling function. Okay, and the set of atomic propositions. So this is a 5 tuple. So in this example, the set of states are 0 through to 8. The atomic propositions are north, south, red, north, south, green, east, west, red, east, west, green, and what exactly is the transition relation? R is a subset of S cross S, which you can see. R is a subset of S cross S. So that means, for example, we have a transition from 0 to 1, we have a transition. So R equal to 0, 1, 0, 3, da 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 da. And L is a labeling function. L is a mapping from S to 2 power of AP. So this is the power set. So that means if you take any arbitrary state, so L of 4 is essentially mapping of state 4 with 2 atomic propositions, which is north-south is yellow and east-west is red. I still have half an hour to go. After half an hour. So is that clear? So that is essentially a kind of a formal mathematical model. This is nothing but a finite state machine model, except that we have got atomic propositions labeling, or atomic formula labeling the states. And once we have this, we can actually do proofs if we have temporal logic formula. So let's see how to write temporal logic formula. So essentially what we can do is the set of temporal logic formulae are a collection of 2 types of formula. They are either state formulae or path formulae. And the set of CTL formula are only the set of state formulae. They are not path formula. Path formula are not, path formula can be part of state formula, but path formula cannot be a CTL formula. So what is a state formula? A state formula is one which holds over states. A path formula is one which holds over path. What exactly is a path? A path is an infinite sequence of states, say S0 to S1, S1 to S2, da da da, ad infinitum is a path. Or for example, S0, 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 ad infinitum is also a path. So any formula that holds over a path is a path formula. Any formula that holds over a state is a state formula. And the set of all state formulae are CTL formula. Path formula are not CTL formula. Now this can be explained using the following diagram, and then we will look at some examples. So let's assume that my set of atomic formula, set of atomic propositions AP is some propositional formula P1 and propositional formula P2. Okay. Now, propositional formula means pure Boolean formula. That means P1 can be either true or false. Likewise, P2 can be true or false. Okay. So I've got 2 propositional formula. And then from these propositional formula, using standard propositional logic, I can build more complex formulae. And when I build more complex formulae also, they are state formula. So here I'm using an automata to describe the CTL syntax. This is just an automaton. And as long as I reach this accepting state 1, I have formed a correct CTL formula. So let's see. So any atomic proposition, say P1, is automatically by default goes to the accepting state, is a state formula. So P1, I can write P1, and then this is a CTL formula. Or I can use Boolean connective. I can say P2, this is also a CTL formula. Then I can use Boolean connective or conjunction P1 and P2. So what are the Boolean connective? Not, and, or, and implication. So 4 Boolean connectives. So this is negation. This is conjunction or and. This is disjunction or. And this is implication. What is implication? P implies Q is same as not P or Q. It's just a shorthand. Okay. So P implies Q in Boolean logic is P prime plus Q in Boolean logic. Okay. So that means I can take P1 and P2, and just P1 and P2 is in the accepting state. That is a state formula. Now, how do I actually, so far, this is not really a temporal logic formula. This is just a pure Boolean formula. In Boolean logic, this is P1 dot P2. But by default, all these Boolean formulae are also temporal logic formulae. Now let's see how to create proper temporal logic formula, which gives some temporal meaning. So for example, now I can do, what I can do is I can prefix this formula P1 and P2 with any of these 4 temporal operators. So what are my temporal operators? I've got 4 different temporal operators. These are X, F, G, and U. X stands for in the next state operator, in the next state. F stands for in the future. G stands for globally, and U stands for until. Okay, I'll explain until a little bit later. So what I can do is I can take P1 and P2 and I can prefix it with, say, I say in the future P1 and P2. Now this one takes me to this set of path formula. Now this is a formula where I'm saying this formula holds over some path where in the future P1 and P2 holds over a path. So that means this will hold over a path where in the future P1 holds and P2 holds. So I can say over this path in the future P1 and P2. People can stop me at any time. If you are not following, please ask me. Okay. So now I have created a path formula, but this is not a CTL formula because we are not in the accepting state. Now, if you want for this formula to be a CTL formula, you have to use a path quantifier. So what are the 2 path quantifiers available? This stands for along all computation paths starting from this state, or there exists a path starting from this state. So I can say along all paths in the future, P1 and P2. So this was a path formula. Now this becomes a state formula. So then I go back. I am in the accepting state. So now I have created a CTL formula which says along all paths in the future, P1 and P2 holds. Along all paths in the future from the current state, P1 and P2 holds. Okay. So this can be formalized using these 2 definitions. But before that, did people tentatively get the idea?
Yes, sir. Yes.
So then, as I defined in diagrammatically, I can formally define. So you will see some kind of mutual recursion in these formulae. So what's a state formula? Any atomic formula is a state formula. Then how can I build more complex state formula? I can take 2 state formula. So we built 1 state formula along all paths in the future, P1 and P2. I can combine this with another, suppose I have another state formula, which is there exists a path P1 until P2. Okay, so this is another, this is a formula EU. P1 holds until P2 holds. So what is the idea of P1 holds until P2 holds? That means I have a path where P1 holds, until in the future P2 holds. Then I can say P1 until P2. If there exists one such path like this from the current state, then I can say that there exists P1 until P2. So I have 1 state formula. What's happening? I have 1 state formula along all paths in the future P1 and P2. Another state formula, there exists a path P1 until P2. Then what can I do? I can combine them. I can say this or this. Either this holds or that holds. So I can do that. So that's what this is saying. If P1 is a formula, if Phi1 is a formula and Phi2 is a formula, then not Phi1 is a formula. Phi1 or Phi2 is a formula. Phi1 and Phi2 is also a formula. What kind of formula? These are all state formula. Also, if Phi is a path formula, then there exists a path phi, and along all computational path phi are also state formula. This is explained here, where you can take a path formula, prefix it with a path quantifier, you can get a state formula. What is the definition of a path formula? It is rather simple. You take any two state formula, if phi1 and phi2 are state formula, then in the next state phi1, in the future phi1, globally phi1 until phi2 are path formula. I could have also said in the next state phi2, in the future phi2, da da da. So if you take any state formula and prefix it with a temporal operator, that becomes a path formula. So let's look at some examples of CTL formula. For example, if I want to say that every request is eventually acknowledged, then this can be represented as a CTL formula like this. Acknowledge is a atomic formula. Request is an atomic formula. So they are CTL formula. In the future, acknowledge is a path formula. This is a path. And then along all computational paths in the future is a state formula. So this whole thing is a CTL formula. Now request implies that this is a, because request is a state formula implies another state formula is a CTL formula, that's all good. Then if I say globally in front, that becomes a path formula. And then along, if I put a path quantifier, this whole thing is a state formula or a CTL formula. What is this expressing? That is saying that every request, whenever there is a request, eventually that is acknowledged. So, for example, a diagrammatic representation of the CTL formula, along all paths globally, there exists a path in the future P, could be represented as a kind of a computation tree like this. So if P holds here, I can say exist a path in the future P. Because of that, I can say exist a path in the future P, exist a path in the future P. So here I can say along, because everywhere EFP is there, I can say along all paths globally, EFP holds. Okay, so I will again pause and I will take any questions you might have. Any questions? So someone asked me about a little intro to temporal logic. So that's kind of a brief intro to CTL. LTL is a simpler form of temporal logic where you are only reasoning over a collection of paths. Okay.
Jhalak, is it clear? Or you want to ask?
Yes. Sir, just one thing. I mean, this kind of this temporal operators like X and F and these operators, sir, how they, I mean, how they impact the performance of the overall automata? Because without this operator, we are simply working on a finite state automata. But how these operators are actually impacting, or there is some physical that triggers this kind of response?
No, it's not like that. These automata are used to express properties. For example, I can, for that, okay, I'll show you. These automata and the associated temporal logic can be used for performing model checking. I'll show you. So, for example, I can take a property along all paths in the future. There exists a path in the next state where east-west is green, right? So what is the meaning of this formula? That means if eventually east-west light becomes green. Okay. Now, if I want to prove this, then what I can do is I can perform a very simple technique of reachability to verify this automata step by step, where I can start by checking where east-west light is green. I don't know why this is not working. Okay, so I can iteratively check. So these are primarily used for, yeah, these are primarily used for checking checking if a given formula holds over a model. So there is nothing like nothing like the question you are asking. So the temporal logic is a specification language, and the automaton is something you can extract from a design, and then you check if a given specification holds over a model or not, and you can check that iteratively. Did I answer your question?
Yes, sir. I mean, one misconception was clear. I have developed a misconception.
So basically, so what I could do, I'm not sure why this annotator is not working. Maybe my pencil ran out of battery. Okay, anyway, so that's the idea, that you are going to check if the model satisfies a given property or not by iteratively checking. But this is a very simple model checking example where basically I'm simply model checking if a formula holds over a model or not. Okay. So now I'll switch back into my other device to show you a few tools and show you some videos, and then we'll conclude.
Okay, sir.
Feedback link, please.
Is that okay now? Can you hear me, Lolatendu?
Yes, sir. Yes, sir.
Okay. Okay. So so basically, just to explain, if you can see my screen, let me see if I'm sharing present now. Screen share. Okay. So essentially, as I was explaining, you can take a temporal formula and you can iteratively search using some kind of reachability. For example, if I want to say where east-west is green, I look at states where east-west is green, right? So that's one state, that's one state, that's one state. 1, 5, and 8, east-west is green. Then to check where in the next state east-west is green, I can do backward reachability. So if east-west is green here, from 0, I can say in the next state east-west is green. Here again, I can mark next state east-west is green, next state east-west is green. And then negation, all other states have negation of that. So, and to check EG, that's a little more complex, because EG means along all paths, globally paths are infinite. So essentially we have to compute strongly connected components. So strongly connected components you find, these are essentially cycles, and so on and so forth. So you can, so to summarize, temporal logic expresses properties over infinite paths and branching futures, particularly CTL, and then you can express you can do proofs using model checking. But this is a very naive method of proof. The complexity is exponential, because you'll notice that the complexity is size of the formula times size of the model. Now, size of the model, if you have got concurrent components, will be huge. So you cannot do explicit state model checking. You have to do other kinds of techniques like symbolic model checking. I was talking about timed automata. Let me explain a little bit about timed automata. So here is an example of timed automata to model the heart as a randomly operating heart, which is beating between some minimum waiting time and maximum waiting time. So what I can do in a timed automaton, I have a single location. This is a randomly operating ventricle. There are two transitions. So the first transition is either so here I'm using a question mark as input and shriek as output. So VP is an input channel where the pacemaker is pacing using VP. That's why it's an input channel. So essentially the invariant in this location is when I start execution, the value of my clock is 0. And as long as the clock is less than some maximum waiting time, then I remain in RV. Before this invariant becomes false, I have to take either this transition or this transition. Let's look at this transition. This transition will trigger and has to trigger before maximum waiting time, before this time. Either this has to trigger or this has to trigger. This will trigger if the pacemaker provides a pace. And if it provides a pace, I will initialize my clock variable x to 0 again, go back and wait again in RV. Alternatively, what can happen is I have a guard which says x is greater than v min wait. That means this is kind of a lower bound that only after this minimum waiting time, I am after this, but before maximum waiting time, in between this interval, in this kind of open interval, what I'm going to do is I can output an HV pulse randomly. So, and then initialize my clock. So here is one trace. This transition triggers at this point where I satisfy the lower bound and the upper bound. Then I initialize my clock to 0. Next time, so this transition has triggered. Then next time, basically this triggers earlier, but again after min wait, but before max wait, I initialize it to 0. And third time, VP triggers, this one triggers. Again, this can trigger any time before this one, and that is satisfied. So here, the heart is beating randomly between these two intervals, and the pacemaker can pace before that time lapse expires. So this is how, using a single location, we can model a complex system as a timed automaton. So basically, then we can model the heart as a random heart. We can model the pacemaker and the pacemaker logic as a pacemaker controller as a collection of timed automata, and we can verify this in a model checker. For example, maybe I can show this to you a little bit, and I can also show you language. Is there a new presentation after me? Is someone else presenting?
No, sir, no.
Can I take 5-10 minutes more?
Yes, sir, definitely.
So first, Lolatendu, you asked me about a tool chain for synchronous programming. So this is an open source software from Kiel University called Keeler. Using which safety critical systems can be designed using the synchronous approach. So for example, here I have created a model. So here the beauty of Keeler is that you can write code using some simple state machine language called SC. So this programming environment is called SC charts, and this can you see the screen properly? Is it visible?
Yes, sir, it's visible.
Okay, so this is a synchronous program which is modeling a 3-bit counter. Okay, now a 3-bit counter you can model using 8 states. Going from 000 to 111 as a naive 3-bit counter, but here what I've done is I've used 3 concurrent state machines to model individual bits, bit 1, bit 2, bit 3. Okay. And these concurrent state machines are using the concept of synchronous programming to emulate this concurrency. Now, this program is actually an incorrect program, because when the counting is done, this is outputting end, and this one is what is known as a strong preemption transition, which will trigger only at the start of the tick. Now, if I compile this, this program will not compile. This will generate a compilation error. So either synchronous programs are rejected by the compiler, then the program is incorrect, or if the compiler accepts the program is automatically correct. That means there are no race conditions, unlike, you know, in multi-threading, asynchronous concurrency, and so on. So for example, this program, if I try to generate C code, I should get an error. So let me see C code, and then it is, the compiler immediately says this is not compilable, there is a scheduling error. So how do I fix this in SC charts? I know this design, but this is a causality error, because this transition can trigger only at the start of the tick, and this can trigger only if this executes, but this will execute only generated at the end of the tick. So there is kind of a paradox. So this can be removed by making this a weak preemption transition. And if I save this, so as you can see, when I save my code, my diagram changes. Now this is a weak preemption transition. And now if I generate C code, this is fine. I generated correct C code. Now I can execute this C code tick by tick. Basically, that's what I wanted to show you. So I can execute this tick by tick. So what this is this counter is counting the occurrence of input A in the environment, and the counter starts counting when start is given and stops counting when end is generated. Okay. B, C, and end are internal signals for communication among these state machines. They are not visible in the environment. So let's execute this. So you can see as I execute, I'm in not counting. Now if I give start, then I go into counting, but you will notice that there is some concurrency happening. I'm in a higher level state called counting. I'm also in A1, B1, C1 simultaneously. And now I will be counting the number of A's. So I give my first A, then I'm in A2, B1, C1. So that means I'm in 0, 0, 1 state, right? So I was initially in 0, 0, 0. Now I'm in 0, 0, 1 because first A has happened. Then I count the next A. Now this is where interesting stuff happens. You'll notice that these two concurrent state machine, these two transitions are triggering simultaneously because of tick-oriented execution. That means A produces B, and B is instantaneously consumed. This is known as the synchrony hypothesis, which says that there is no delay from A to B, and B is broadcasted. So these two transitions happen synchronously, concurrently. And then if I give the next day and so on and so forth, these transitions will keep on triggering until you notice here now 3 transitions are triggering. A outputs B, B outputs C, and that takes this transition. So I go from A1, B1, C1 to A1, B1, C2, and so on and so forth. Until I give 8 A's. And when I've given 8 A's, now you'll notice something very interesting, that end is generated by counting. That will trigger preemption or will kill this automata and will bring control back into not counting. So this kind of programming environment is similar to SCADE, not identical. SCADE has many more features. But SCADE supports MATLAB Simulink, like modeling of more complex things, like not just state machines and hierarchy and concurrency, but other things. For example, here I could model a pacemaker through this. So for example, I could model a VVI mode pacemaker like this, a very simple pacemaker model, where I have two controllers to control two timers of my pacemaker, one controlling the VRP timer, other controlling the LRI timer. And from this, actually, I can generate C code, and this C code can be embedded on any microprocessor. So I teach a embedded system third-year course where students design this kind of pacemakers, and then they embed it into the NIOS kit, and then they test it using a hard GUI, where the hard GUI is interfaced using the UART. The hard GUI runs on the PC, the NIOS runs the pacemaker, and then they can test their design. Okay, I was just showing you some of the things we are doing, but there are more stuff. Okay, let me show you. So I was in lecture 3. Here I wanted to show you that video. Let me show you that video on YouTube. So this is the heart on chip setup. This is a 3D printed heart with the LEDs, and each of these denote the paths, and these are the nodes described as hybrid automata. And for a normal heart, the conduction is going from the atrium to the ventricles normally with proper timing delay. But if there is a AV conduction block, there is a AV node. If that node is blocking, then without pacemaker, you will see that timing is desynchronized. Likewise, if the sinoatrial node, if the normal pacemaker of the heart has failed, you will notice that the timing is desynchronized. So these are all kind of behavior which we can trigger by parameterizing our model, by giving some inputs on the FPGA board, by setting some parameters, by flicking a switch, for example, we can induce different kinds of disease states in the heart. And we can connect this heart to a pacemaker to show how the pacemaker could correct this kind of behavior. So we can connect it to a pacemaker. Let me show you that setup to show correct behavior. So that is one thing that I wanted to show you. So we have tested a Medtronic pacemaker using this approach. Now finally, I think that I have taken 10 more minutes of your time already. Do you have any more questions? So no, I was also talking about our COVID-19 paper. So if you are interested about that, I will send a link to that paper. Now, there are a lot of references on our slides. So, for example, if you want to learn about model checking and temporal logic, there is a book I wrote with one of my previous PhD student who is a professor in a neighboring university in Auckland. This book is called Correct by Construction Approaches for System on Chip Design, where there is a full chapter on model checking and module checking, where we illustrate it using SOCs, but in general, we also introduce temporal logic model checking. If you want to know more about kind of model checking, there is a very good book by Edmund Clark as well, but this is a broader book. This book is much easier to follow for engineers. If you want to know about cardiac pacemaker and pacemaker design, this is one of our early papers. Okay, so that sort of concludes everything I wanted to present. Is there anything else?
Sir, good afternoon, sir. I have one question. Like what in Killer we are using a system that finds the state automata and all. How many maximum states can we take?
Okay, that's a very good point. So if you are using finite state machines, Model checking is very scalable. There was a paper which was written by a person called Kenneth Macmillan, 1990, where he showed how to use model checking to verify. The paper is called 10 power 20 states and beyond. Okay. So in 1990, Kenneth Macmillan verified 10 power 20 states. Okay. So if you have just normal finite state machines, then verification is very, very scalable. Then this technique is called symbolic model checking. But nowadays, people are verifying large programs, and there are many, many techniques like SAT, like SMT, which are used to verify large state spaces. Hughes programs, programs with pointers. So software model checking is also becoming kind of industry grade. Any other questions? So let me see if there are questions in the chat.
Sir, I have a question.
Uh-huh.
Like in the heart on chip, we have nodes. So are they comprises of any cores?
What do you mean cores?
What is
You
the
mean parallel
architecture of
execution?
nodes?
No. So the nodes. So look at hybrid
What
automata
is
modeling language. So let me see if that is cited in the other presentation. Just give me a second. Okay. So this is a good paper to read. This is
like in the video
ACM.
they are showing some kind of LEDs.
Sorry.
Sir, in video, like nodes are shown with LEDs.
Yeah. I will come
So
to that. I'm
like
coming to that.
any cores are connected.
No. Just hold on.
Like what is the architecture of a node?
Hold on. I'm coming to that. So first, I would request, can you see my screen?
Yes, sir.
So this is
Yes.
a paper. This is one of our early papers towards emulation of cardiac conduction system for pacemaker validation. Eugene was my postdoc, and basically, if you read this paper, that will give you more ideas about what I'm talking about. How to model all these examples. This modeling stuff is sort of initially presented in a lot more detail. I presented this dynamic behavior. So when I'm talking about hybrid automata and these nodes, these are logical mathematical behavior, and you can find, and these are described using a programming environment called HAML, hybrid automata modeling language. So again, let me see where that is. Yeah. So let me see if that's cited. Somebody's not muted and talking. So this is a paper, modular code generation for emulating electrical conduction system of the human heart. So this appeared in date 2016, but there is a more recent paper, ICCPS 2020. So we describe the system using HAML language, from which we can generate either VHDL or C. So these nodes are all compiled away into a network of finite state machines. Okay. And these can be executed they're all executed on an ARM core combined with some FPGA fabric, where in the FPGA fabric, some of the FSMs are executed in parallel, true parallel. Other FSMs are executed purely sequentially on an ARM Cortex core. Did I answer your question about the architecture?
Yes, sir. Yes, sir. Yes, sir.
So read the date paper
Okay,
and the
thank you, sir.
subsequent ICCPS paper.
Okay, thank you, sir.
Okay. Any other questions? Okay.
Sir, I think there is no question.
Thank you very much. Thank you so much. So I think that is good. Lalchendu. My wife has already called me for dinner twice now. It's a
Okay.
Saturday here. It's a holiday.
Yes, sir.
But anyway, thank you so much. And
So, sir, I
yeah.
want to thank you. I want to thank you very much for this nice presentation, and we have gone deep to the formal verification and CTL LTL also. So, so we look forward to you to host you here at NIT Jalandhar in future, if you permit us.
Thank you. Thank you, Lalchendu. Thank you.
Thank you. Thank you.
Bye. Bye.
डाल दूंगा।
Okay.
Sir, can we get a recording of these sessions?
I'm not sure about the recording. We can share the PPTs, but I'm not sure about the recording. So we have to take the permission from the authorities. Then we can share the uh, recording. So link is feedback link is available on Google your chat box, and I think there is no need to be panic about the feedbacks. Okay, so why you are so panic about feedbacks? And we will provide you at the end of the session. We already tell you about these things. Okay, so now you can fill that particular feedback. Okay, and next session will be at the 4 p.m. So we can meet at 3:50. And if you have any issues, we already give you contact numbers, and there is a mm, I think WhatsApp group is also available, and for YouTube session, and we will share the feedback link on the YouTube link also. So I think we will meet at 3:50 for the next session. And thank you for attending the session. Next speaker is Parashar Sridhar sir at 4 p.m. and he will continue from his last lecture, and that's it, I think.
Okay, so shall we start the lecture now?
Yes, sir. So, welcome to this session, and we have Professor Parasar Sridhar with us, and he will continue his lecture from the last session where he left us. Okay. So, sir, welcome to you, and you may start
Mhm.
your lecture now. Thank you, sir.
Okay. Yeah. Thanks for thanks for inviting me. And this is my continued lecture from yesterday on simulation-based verification of cyber physical systems. So yeah. So yesterday I talked about a lot of theory, but I didn't go into any one of these any examples. So today I want to start the demo today I want to start the lecture by showing an example of an actual verification problem. So here I have, this is a simple system here. I'm guessing that all of the students can see my screen. Unfortunately, I can't see your faces while doing the presentation, so it's kind of a trouble. But yeah, so I have say two variables, x and y, and the difference that influences these two is given as x dot equals to y and y dot equals to minus x. So it is written in the form of a matrix. So x dot y dot is written 0, 1, minus 1, 0 times x comma y. Right? So here is a set that is represented in a star notation. So if you look at the equations on this side, these actually tell you what are the equations. So if so, let me align this and make it more clear. So here, okay. So notice that here I have so I have minus 1 0 1 0 minus 1 0 0 1, which means that x, the value of x is currently equal to 1 times x0 plus 0 times y0, and the value of y is currently equal to 0 times x0 plus 1y. So essentially this means that xy is nothing but x0 y0. So here I use x0 y0 to represent the predicates. So here, if you remember from yesterday's class, I have a star representation. Essentially, I have a set, and I have here, and I have a basis vector, right? And the set is represented as alpha 1 times the first basis vector plus alpha 2 times the second basis vector. So what I did not say clearly is the center can be outside the set as well, right? It is not necessary for the center to be completely in the set. So right now, maybe center is not the best name. We are now trying to call it as anchor and generators. But here, you can see that in the equations now you can see that the upper and lower bounds on the first quadrant are essentially the lower bound is 2.36 and the upper bound is 5.04. And similarly on the y, it is upper bound is 3.02 and lower bound is 0.02. What would happen if I align them exactly like this, right? You can see that the lower bound on x is 0, the lower bound on y is very close to 0, x is 2.67 and 2.66. So this is one way. So constraint is constraint based on, yeah. Is everyone able to see this change in the set? Hello?
Yes, sir.
Yeah, are you guys able to see the changes in the set when I'm moving this green thing here?
Yes, sir. Yes, sir. Yes.
Okay, yeah. So okay, let me do one thing. So how would I compute the reachable set of this specific set? Okay? So let me move the set away, and when I move the set away, all that changes is the predicate changes, right? To actually compute the reachable set, what do I need to do? I need to generate one trajectory from the center, one trajectory from one basis vector and another trajectory from the other basis vector. Right? It turns out that in the case of x dot equals to x, x dot equals to y, and y dot equals to minus x, the point 0, comma 0 is a stable equilibrium. That is, you need not generate any trajectory from the origin. It is any trajectory from the origin stay only there. That is what is called as an equilibrium point. So I need not generate the trajectory from the center, but I generate two trajectories from the from each of these basis vectors, 1, comma 0 and 0, comma 1. Right? Let us see what happens when I generate these trajectories. Right? You can see that I'm generating these trajectories, and each of these trajectories changes by some value. Right? And at this particular point, so I stopped at an arbitrary point of time. Right? So let me make this. Okay. Right? Okay. So yeah. So here I have stopped the trajectory at some point of time, and notice that the trajectory 1 goes until minus 0.71, 0.70, and this exact value is part of the. So I'm multiplying all the coefficients of alpha 1, which is the coefficient for x, by this specific vector. Okay? Similarly, I'm multiplying all the values of alpha, which is the second, which is the coefficient of the second basis, with the exact vector, which is minus 0.7 and minus 0.71. Right? And what we'll get indeed is the set representation after time t. So this is Pareto representation which will set after time t. Now, advantage is, as I mentioned before, you need not change or generate any new trajectories. So whenever my mouse is on one of the right hand extremes, so you can see that this value is going to change, right? So now the value of minus 7.88 is going to go from minus 7.88 to minus 10, right? And even in those cases, right? So when it is minus 10, notice that I did not generate any new trajectory, right? What I did was change in the predicate, and the reachable set changed immediately, right? So, so this is one way. So this is the case of the harmonic oscillator. There are several other examples. So this is one of the nicer examples called damped oscillator. The dynamics are somewhat different. Dynamics are minus 0.3x plus y, and y minus x minus 0.3y. Right? And again, you can start from any initial set, and if I start generating the trajectory, right, you can see that now the set actually goes towards the origin and is converging. Right? So it's that the state of the trajectory after time t, which is minus 2 minus 0.25, is in the red trajectory minus 0.25 minus 0.2 is part of this the first column, and minus 0.20 and minus 0.2 is part of the second column, and I multiply my coefficients by values to actually get a representation of the reachable set. And as I said before, all I need to do is change this predicate, and my reachable set changes immediately. Right? So this is one demo that I wanted to show you. So here is an example of, I have a simple harmonic oscillation system, and here my reachable set can be computed very, very quickly. So notice that all of this is happening. So this is within JavaScript, and all of this is happening without, I mean, there is no lag, right? So it's similar to as if it is happening in real time, right? So, and again, I'm computing the reachable set not just for one, but for all the intermediate steps until some time t, and I'm representing all of them in this green region. Now, here is something peculiar, right? So if I bring the green region here, and if I make it somewhat large, right? So after time t, notice that the reachable set is contained within the initial set. So what does it mean? It means that all the states that are reached, or all the states that are reachable until now, gives you an idea of over approximation of the reachable set, not just for bounded time, but for unbounded time. If you don't follow that, it's okay. But I can. What I want to tell you is you can also do unbounded time analysis. You need not have a certain bound for reachable set computation. But this is what this is one demo that I wanted to show you to give you an intuition as to how the exact method which uses simulations for verification, especially for linear dynamical systems work. Right? Um, does anyone have any questions in this part?
No, sir, no issue.
Mm-hmm. Can you hear the voice properly?
Voice is little bit breaking. Not
Okay. Now,
not always, but sometimes.
now is it better? Is it better now?
Yes.
Okay. Okay. So I'll probably do this. Okay. Okay. Sure. So I'll start from here. Mhm. Okay. So I'll continue this and I'll start the um, Okay. So now, yesterday what we looked at was first is we looked at how we compute the reachable set, and second thing is we looked at how do we handle invariance for computing reachable set for linear hybrid systems. Today, I want to talk about something much more interesting, which is how to handle the discrete transitions for linear hybrid systems. For those who just to catch up, let me go to the next slide. That explains this. What happened to my slides? There was some. Hey, wait, I think the slides are. Okay, so let me. I think there was something wrong with the slides. Okay. Okay. So yeah. So yesterday we discussed that a hybrid automata is basically a cyber physical system where you just don't have one controller, but you have several controllers, and you switch between one controller to the other based on the guard conditions. And in each of the sets, you satisfy some invariant. Right now, in what we looked at was how to propagate constraints from the invariant to actually how to do constraint propagation in order to complete the reachable set. And today, what we look at is what are some of the challenges in handling the discrete transitions. Okay. 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 So before I go on, let me tell you a short story about how NASA lost close to $110 million. Right. So what actually happened is NASA has several satellites upon Earth, and what happens is routinely they have to perform some sort of a maintenance and rendezvous. And so this rendezvous is supposed to actually help either the satellite to correct its orbit or to install some equipment in there, or maybe sometimes to decommission the satellite or to retrieve something important. So just to give you an idea, when the digital cameras weren't invented in the 40s and 50s, whenever a satellite used to go up in the air and take pictures of Earth, they actually used to record that on a film, and the satellite has to throw that back onto the ground, right? There are several such satellites still up in the air, right? So we haven't fully decommissioned them. So this is satellite rendezvous is one way to slowly decommissioning one of them at a time, so that in future we'll be able to more and more interesting advanced satellites. So what happened was there was a NASA satellite called MobileCom, MUBLCOM, and that spacecraft was supposed to meet with that specific satellite. What happened was there was an error in the design itself of this rendezvous mission, and the mission failed. Instead of the DART spacecraft meeting or rendezvousing the satellite, it actually crashed into the satellite and completely destroyed both the spacecraft and the satellite, right? So this is a horrible situation to be in, because you not only lost the satellite, fine. I mean, losing the satellite is one thing. You also lost the spacecraft, that is worse. And finally, you have now a lots and lots of space debris, which will take where it is very difficult to account for them, and it is very difficult to clean it up in the later stages. So this should never happen again. So let us go into the reasons why this actually happened. So if you look at the spacecraft model, did was it had a specific switching scenario. So the spacecraft, which is shown in the blue here, it had to go to the target, which is shown in the green. Right now, if you are trying to go somewhere, the obvious thing to do is you first want to get to the vicinity of the object, and after you get to the vicinity of the object, you apply some more advanced controller. So that's exactly what happened. There is a FAR controller which takes the spacecraft from very far, or which is very, very far from the satellite, to a closer region. Right? That is called the FAR controller. Now, when you are in a region that is close to the satellite, there is a switch that happens, and then you go into the approaching mode. So in the approach mode, you apply much more carefully fine-tuned controller, so that you don't meet with the satellite with too high speeds. Like this is, for example, whenever you drive from one place to the other, you go at a much higher speed in the highway, because you know that in those places everyone drives in a certain way. Whereas if you are driving in the streets, you are not. Everyone drives in a same way, that they will drive less than, say, something like 30 kmph, right? Because you don't want. There are always accidentally people are coming in the way, and so on and so forth, right? So similarly, it has a FAR and it has an approach mode. What many people, there was a deliberation to think of this abort mode. So this abort mode can happen whenever you want to. So there should always be an abort button for everything, right? Why? Because maybe you realize once you start the mission that this mission was a bad idea and you could do it in a better way. In that specific case, you need some time frame to abort the mission. So what happens is, in abort the mission, when you press abort, what happens is the rockets that are guiding the spacecraft, which is shown in blue here, they will stop functioning, and the spacecraft would go on its own path, right? So whenever the spacecraft stops functioning, it has its own path, right? So that's what happens. Now, one thing, the design flaw in this specific approach was that they did not anticipate the fuel to be over before the time that it actually happened. So the reason why this specific disaster happened was that they were still, the spacecraft was still in the far mode and did not go into the approach mode. But then what happened was, in the far mode, the spacecraft ran out of fuel. So when the spacecraft, it changed to abort mode, and in the abort mode, it couldn't stop itself from colliding into the satellite and causing the huge damage of property and lots of space debris. Right. So now, how do you solve this specific problem? Now, a whole lot of non-determinism. Right? So if you look at the behaviors of this three-mode hybrid automata for the spacecraft, this button can be pressed at any point of time. Right? So you would want to have a specific method where you are able to handle such a high uncertainty, this specific transition. Right? And similarly, even when you are approaching, when you do up, you need not be with the spacecraft. Now, our solution is basically to compute the reachable. So each of these reachable sets are successively better over approximation of the reachable set. Notice that here you can see a white region opening up. And why is that opening up? It is because when I do a more accurate analysis, then it shows me that no, indeed these regions in the white are not actually reachable, but they are an artifact of the over approximation that you are doing. Right? Now you can actually see that the entire region in the red is in the white zone. So which means that I have performed the reachable set computation, and I'm able to prove that the set from of the specific hybrid automata does overlap with the unsafe set. Right? Is this example clear?
Yes, sir. It is clear.
Okay. Okay. So now, as we have seen yesterday, what happens when you perform, whenever you want to perform discrete transitions? So discrete transitions are enabled whenever the reachable set overlaps with the guard condition. Suppose you have a specific reachable set theta, right? Suppose it overlaps with a guard at some of these regions theta I. Reachable set is now what I call the reachable set as the sequence of states that I compute. So this intersects with the guard, and let me compute the intersection as theta I1, theta I2, so on until theta I. Right? So clearly, whenever there is a guard, there is not just one discrete successor, but each of them a L successor unit. Right? What will happen is, after M transitions, each of these will have L more successors, and each of them will also have L more successors, right? So this will create some sort of an exponential blow up that we just cannot tolerate, right? So we don't want to have something close to L power M exponential blow up, but we need to have a set representation, or we need to have so we cannot handle all of these L power M individual reachable sets, right? So we need to have some other way to improve the order of over approximation, right? So one of the techniques that people often use is to do aggregation, right? So let me go to So what happens when you do aggregation? So suppose that I have so in aggregation, what is I have K overlaps with the guard sets. So theta I1, theta I2, so on until theta IL. All of these are over approximated using a single initial set, and then we compute the reachable set of that single initial set in future. Right? So what that does is it reduces the number of sets to keep track of. So instead of the L individual sets, because you're over approximating all of those L just by one set, you need to keep track of very few number of sets. But the problem is that this introduces a lot of over approximations that we can never get rid of. So the reason why we get over approximation is because most of the times the reachable set or the sequence of states in the reachable set, when you perform the set union of them, you will get a non-convex set. And whenever you have a non-convex set, and when you're approximating them, when you're approximating that by a convex set, then you'll always have a problem. As in, you'll always get an over approximation, and your over approximation only gets worse the more the number of sets that you're aggregating. Now, there is a secondary effect which is called the wrapping effect. Whenever you do aggregation, and whenever you do aggregation, you lose the information or you erase the difference between theta I1 and theta I2. Right? So when we do aggregation, we say that all of these are contained in just one set, and that one set, I'll compute the reachable set of the aggregate of that reachable set. Okay? Now, so the problem is when I compute the reachable set of the aggregate set, that might introduce new discrete transitions that do not have exact concrete counterexamples. That is because the reason the aggregation is not because it is the most accurate one. I'm just trying to save some computation, and that's how to do aggregation. Right? Because of this aggregation, I will introduce an over approximation, and that over approximation can improve or can induce further discrete transitions that do not have any specific, that do not have any concrete counterexamples. So we don't want such aggregation where you cannot. So when you say that a specific discrete transition can be taken, you do not want to have a scenario where that discrete transition cannot still be taken, but still that is part of your reachable set. Right? So in some sense, if you perform aggregation, if you do not aggregation, you have too many sets to keep track of. But if you perform aggregation, you will introduce a lot of uncertainty. Right? So it's as if damned if you do, damned if you don't. Now, how to get rid of this? So what we'll do is let me illustrate with this very specific concrete example. Right? So here we have far, approaching, and abort. Right? So let us take the condition where we are going from far to abort. Right? So now suppose that my reachable set is from R1 to R5, and the guard condition is shown here. Right? So what would happen is region R3, region R4, and region R5, all three of them can take the discrete transition. So once I compute the reachable set of some theta in the far mode, now I need to compute the reachable set of R3 in the abort mode, R4 in the abort mode, and R5 in the abort. But then, what if abort also wants to have some more discrete transition? You cannot have them, right? So instead, so as I said before, the number of for some reason the animations aren't playing good. So let me delete all the animations. Yeah, it's a problem with the animations actually. Yeah. Mm-hmm. Yeah. I think it's the animations that were causing the problem before. I couldn't see some stuff. Okay. So now, so if you want to do aggregation, so ideally you would want to have you can't keep track of all those m power n statements, right? Or the exponential increase in the regions that you need to keep track of. So one way to kind of intelligently do aggregation is to represent R3, R4, and R5 all part of some gray set. which is much more accurate, but that is cheaper. Right? Now, what we do is we present or we have two specific type of aggregation mechanisms. One of them is what is called as a template-based aggregation, where we pick some specific templates. So we pick directions D1, D2, so on until Dk, and we compute over approximations of each of these regions along that template. Right? Now, when we do, so in this particular case, I'm taking the coordinate, the orthonormal axis direction. So I'm computing the bounding boxes of each of these regions. Right? Once I compute the bounding boxes, the aggregation of all of those is I'll just take the maximum and minimum values of these templates for each of them. Right? Once I do that, I can compute an over approximation of the reachable set. This is creating a havoc. My slides are all messed up. I don't know what happened. So, okay. Yeah. Okay. Okay. As I said before, whenever you do any aggregation, in this particular case, you can get a very, very significant over approximation, right? So here you can see that although the union of R3, R4, and R5 are a tiny space of the region, because you are using the template directions to compute the bounding boxes, you are including a lot which in your reachable set which were not originally a part of it. Right? But there is one advantage with the template-based aggregation though. One of the advantages is if you want to improve the order of over approximation, what you can do is we can say that no, this over approximation is too conservative. So let me come up with a slightly less conservative over approximation. In that case, you can choose to aggregate R3 and R4 or R4 and R5 and get two smaller successive over approximations of aggregation. And so here you're increasing the number of states to keep track of, but you're only doing this whenever you want to do them. So it's not a compulsory thing. So you can recognize that whenever your template-based over approximation is causing way too much conservative over approximation, then you have at least the ability to dynamically scale down the order of over approximation. Okay? Now, any questions here?
So, so participants, if you have any question, you can ask.
I'm not looking at the chat window, so did anyone post any questions in the chat?
No. I'm checking the chat window.
Okay. Yeah, anyone has any question until here? Okay, so in that case, let me go to the next aggregation method, which is called the convex hull aggregation method. So here I have each of these regions, but then I can perform convex hull of each of these regions. So for those who don't know convex hull of two sets is basically I pick any point from the first set and I pick any point from the second set and perform a convex combination of them. So if I have sets as, so here if I have R1 and R2, so R3 and R4, I will draw all possible lines or line segments between any of these two, between any point that is in R3 and another point in R4, and those the collection of all those points is essentially the convex set. Right? What we can do instead is we can perform convex hull aggregation which is much more accurate than the template-based aggregation. But the problem with convex hull aggregation, so one of the papers that we use for performing this convex hull operation is this paper on reachability analysis of hybrid systems using symbolic orthogonal projection. So there, this paper actually gives a syntactic method for in convex hulls. That is, you don't need to perform any additional operations as long as you have the equations for region 3 and region 4. That is the half plane representations of region 3 and region 4. You can compute the convex hull without too much of a problem. Right? So, but the problem is that although it is syntactic, it will increase the number of variables. So, more specifically, each and every time when we perform convex hull of m sets, the number of variables will increase by m times. So, that is, if you have n state variables, and as in you will have n predicate variables as well, what will happen is after you perform convex hull of L sets, you will have L times N. Right? So, I mean, yes, it is more accurate, but when you think of successive over approximation, this will only create more and more problems. Right? Why? Because once you perform a convex hull operation, right? Now your set has L times M number of variables. Right? If you have to do aggregation again, it will have L squared times variable, L cubed times variable. So you still have exponential blow up. It's not just in the number of regions that you need to track of, but the number of variables that you're keeping in your representations. Right? So the second problem with this issue is that unlike the case of template-based aggregation, where you are able to successfully deaggregate and come up with smaller aggregations of smaller subsets, you cannot do that in the case of convex hull aggregation. As in, you need to, if you want to say this is way too conservative, let me only just aggregate R3 and R4. You need to come back to the beginning from the get-go and and reperform these convex hull over approximations. Right? So although this works, this has very high penalty costs. And the other thing that I want to shed light on is implementing this algorithm wasn't an easy task. And whenever we implemented this, we did face into some numerical issues. By numerical issues, I mean that although our constraints are indeed satisfiable, the most of the times the linear programming solver said they are not feasible, or it gave some nonsensical answers. So there are some numerical issues in practice, right? So now, okay, fine. When I do aggregation, the second question that I want to find out is, when do I do deaggregation? I do deaggregation whenever I meet the unsafe set, right? But if you think that to do deaggregation, whenever your reachable set reaches the unsafe set, by that time, you might already be late, as in your aggregated reachable set might have accumulated more and more additional transitions before you actually reach the unsafe set, right? So you want to keep track of all earlier discrete transitions, and then you would want to have some method for successfully deaggregating some of the reachable sets that you have aggregated before. So for this particular purpose, we created a special data structure which is called AGGDAG. So this is called Aggregated Directed SIK Graph. So I'll go into this as follows. So suppose that, so again, let us come back to the spacecraft rendezvous. Right? I'm in the far mode, and I can go to the abort mode anytime in between 0 to 140. Right? Similarly, when I go from approach, I can go from approach to abort anytime between 0 to 140. Right? Now, what I do is I start from the far mode, so I create a node which is 0 to 200. Right? Then I realize that I can make a transition to approach within the interval of 100 to 120. So I add a tree in which I create a node for approach and say that I can reach this from far to approach within this time region of 100 to 120. So I'm performing aggregation of all of these states. Right? Then I can also realize that in the entire region of 1 to 200, I can go to the abort mode, and so I add one more discrete transition and say that I am in fact doing a aggregation of all of these individual reachable sets that can go to abort, and I'll start that as my initial set in the abort mode. Similarly, I'm aggregating all of these and starting that as the initial set for approach mode. Right now, if suppose that so from in the abort mode, I have already started out with the aggregated reachable set. In the aggregated reachable set, if I go to the unsafe chance in this interval, then I can say that no, this intersection is because I have created too much aggregation in my transition from 1 to 200. So what I'll do, I'll split them and I'll aggregate only the regions from time period 1 to 100, and I don't agree, and then I'll do a second aggregation of all the regions between 101 and 200. Right? Once this is the case, I can show that both of these aggregations are indeed safe. So I need not worry about the case of going from far to abort and in the abort mode going to the unsafe set without any problem. Right? Now I come to the approach mode and apply the same analysis. I'll complete the reachable set. I'll go to abort in the time period of 100 to 140, and in this time period, I might actually encounter unsafe transition from time period 120 to 130. Right? So in this case, I now refine. So this can be because of two reasons now. Right? So it can be because of I aggregated too much at the approach region, that is in the interval of 100 to 120, I aggregated too much, or I have aggregated too much in the transition from approach to abort, which is this window of 100 to 140. So here you have two choices to make. Which one should I refine first? Should I refine this and then recompute two successive abort modes, or I should split this and then do reachable set computation of these two? So this gives us two sets of choices possible. One from the top to down, where you refine so you have found a counterexample, which is potential counterexample. That is, you have a preliminary examination shows that you can go from far to approach to abort to unsafe region, right? But again, this is a preliminary analysis because your analysis can be over approximation, right? So now in this specific chain of trajectories, or in this specific chain of actions, you might have introduced over approximation while going from far to approach, or either from going from approach to abort. So now you have the choice to either go from to either refine this interval, that is, you can split this part, or you can split the interval from approach to abort. Right? Is this clear? Does anyone have any questions in this?
Yes, sir. Sir, I have a question. Sir, so how to check the correctness of?
How to check the correctness of what?
Means suppose this is a model. So if I want to check the correctness of this model, so how to check it? It means are you using any tool like SMT?
Yeah. So no. So I'm telling you that we are doing a reachable set computation, right? So in yesterday's lecture, I gave a specific technique for computing the reachable set computation for this linear differential equations, right? Now I'm telling you that there are issues in this reachable set computation, because so now I have computed the reachable set in the far mode, right? And some of them can go to the approach mode, and then they can go to the abort mode, and then they can go to the unsafe mode. right? So the whole system is based on reachable set computation. In fact, that is the exact demo that I showed in the beginning, right? I'm representing the reachable set as a bunch of polytopes.
Okay. Okay. Thank you.
Okay, so here we have a chance of either improving the over approximation in this region or improving the over approximation in this region, right? So so we have two chances, as in two ways to do this refinement, and we actually implement both these algorithms. We implement the algorithm where we refine from root to leaf and leaf to root as well. So here I want to show you a couple of nice benchmarks. So first is okay, so let me ignore this time taken and all that. So okay, so here I have so this is a gear meshing benchmark for electric vehicles. So what happens is whenever the gear is shifted from whenever a vehicle shifts a gear from one gear to the other, what happens is you can model the shift in the gear as, so here you have a shift actuator which actually moves the sleeve from one gear to the other, as in it physically drags the sleeve from the first gear to the second gear. And when it drags the sleeve from first gear to the second gear, there is some collision that happens. That collision can be modeled as a linear differential equation, right? And this differential equation has resets because whenever there is a collision, there is a bounce that happens. So this is how the linear differential equation is modeled, and we say that sometimes the gear is meshed when some condition is met, right? So here so the behavior of this gear meshing is somewhat equivalent to imagine having a cone and dropping a ball on this cone on one of the on the side of the cone, right? What would happen is the ball would drop there and then it would bounce around this cone, and as soon as it ends up in this horizontal region or in this vertical line, I'm fine, right? So here is I have generated several and these are the so you can see that sometimes it takes a while for some of these behaviors to mesh, right? Now, so after the time of 0.3 seconds, it turns out that all of these do eventually mesh, right? So the question that everyone is interested in is that will this meshing happen within a bounded amount of time if I start from a large initial state? That is, I don't know what my y position is and I don't know what my x position is, some uncertainty in my y and x position. In those cases, will I eventually be able to mesh, right? So our approach actually was able to compute the reachable of all of these, and the second thing is we also want to check that the impact, which is the impact impulse is shown here, it doesn't go way beyond them. If you notice the trajectories, right, for most of them it stops around 20. So you can take these impact impulses for longer time duration. But if it goes beyond 40, maybe the gears will wear out much more quickly and you need to replace them, right? So it turns out that, I mean, ours was the first tool that was compute the reachable set of this specific example. Yeah, okay. So what we did was whenever we do no deaggregation, then we cannot do the reachable set computation. Even when we do the convex cell aggregation, we cannot do that computation. SpaceX, which is one of the state-of-the-art tools, it also cannot do the same size of the initial set that we are dealing with, right? But when we do template-based aggregation, box aggregation, we are able to verify it in times of just in seconds, right? Similarly, if deaggregation from the leaves first or the root first or deaggregation more states, you'll get slightly different aggregation time, right? And here is a number of deaggregation steps that are taken, right? So, what we did was we created new aggregation and deaggregation methods, and in these methods, we are able to verify the safety of some of these GAIR machines. So you can see that the reachable set in this GAIR machine benchmark is provided here, right? So it takes a while for the computation to actually finish. I mean, the reachable set, the time is taken primarily to do all the plotting. Most of the reachable set just happens in 10 seconds, way less of a time, right? What we actually conjecture is that we still think that the template-based aggregation is better, but as of now, we don't fully understand what is the most accurate or what are the best templates for computing that reachable set. Okay? Okay. Does anyone have any questions until here?
Hello, sir. My question is, in discrete transition method, what is the interpolation technique should be used for region of irregular shapes, sir?
So that's a very good question, actually. So technically, most of the time you can use linear interpolation. That works. Go to the SpaceX paper a bit more carefully. They do the linear interpolation method, but they do just to give guarantees, just to give rigorous guarantees. They do linear interpolation between time intervals, but also use some sort of a Minkowski sum bloating as well. So it's not just you just cannot do linear interpolation and be happy with it. If you want to give a rigorous theoretical bounds, you need to do slightly more than linear interpolation. As in, you need to add, you need to bloat whatever set that you get by linear interpolation by some specific quantity, which is again calculated using the differential equation. So most of the times you use linear interpolation because that's the only thing you can. But you also need to do some. You also need to add some more over approximation. Does that clarify the question that you had?
Yes. Okay.
Any other questions?
Yes, sir. Sir, I want to know what are other benchmark aggregation methods available?
Yeah, very
Means
good question.
in comparison to this new aggregation method, what are other benchmark aggregation methods available?
Yeah, very good question. So there is only one tool that, one state of the art tool that we compare with, which is called SpaceX, right? Yeah. So SpaceX is one tool. Unfortunately, SpaceX doesn't have any specific deaggregation method that is inbuilt. Again, reason why we are able to do aggregation and deaggregation much more easily is because we are using a star set representation, right? SpaceX by default does full aggregation all the time. There is no, there is no interest for SpaceX developers to do any of these advanced deaggregation methods because I don't know why, but they do not have any of these deaggregation methods implemented. So unfortunately, we are the only one doing any deaggregation to begin with. If at all, in fact, ours is the baseline now. As in, we showed that you can do deaggregation if you use a good representation, and if at all you do deaggregation, this is how, as in root first or leaf first or deaggregation of more states first. This is the way to progress with the deaggregation. SpaceX, which is one of the state-of-the-art solvers, doesn't have these algorithms already implemented. My guess is there is a new tool which is called Julia Reach, and they are working on integrating some of these deaggregation methods into their tool. but I'm waiting for some of those results to come out as well. So ours is in fact the baseline that we established. Does that answer your question?
Sir, can I know some open source tools where we can implement all those things? Means a lot
Yeah,
of
very good
are
question.
not free.
Yeah,
They
yeah.
are just
So,
asking for.
mhm. So I can name you three tools which are, so SpaceX is definitely one of them, right? And the tool in which we have implemented the gear meshing, we have implemented this deaggregation which is called HYLA, HYLAA. I'll give the references in at the end of the presentation. So HYLA is one tool where the code is open source. The code is actually up on GitHub, and you can download the source. You can use the source very easily. SpaceX is another tool. I'm not sure. SpaceX is open source, but the code for SpaceX is very, very complicated. It is not that easy to go through SpaceX code. The other tool that I can recommend is what is called as Julia Reach, JULIAREACH, Julia Reach. I think it's a collaborative project for many people in Europe. There are some people from Germany involved in it. There are some people from France. There are some people from, if I'm not wrong, some faculty who was in Australia who now moved to UK. He is also involved in that project. So Julia Reach, SpaceX, and HYLA, these are the three tools that I can recommend that are open source, and you'll be able to implement some of these interesting algorithms yourself.
Thank you, sir.
Mm-hmm. Okay. Okay. So let me show you some more. Let me show you some more videos. I wanted to make today slightly less boring because yesterday I was purely. Yeah. Okay. So can you see the screen? Can you see the reachable set computation
Yes, sir.
drivetrain model? Okay. So here is an example of a drivetrain model. So what's happening is I'm computing the reachable set at discrete amount of time. So my initial set. So this is again because the number of variables in the system is higher than 3. I cannot represent all of them in a picture, right? So this is a two-dimensional projection of the reachable set. My initial state is x3 is 0 and x1 belongs to some interval, and I compute the reachable set, and this is the reachable set that is being computed, right? So notice that here initially I was in green mode, and then I suddenly changed to blue. So that blue, it corresponds to a transition in the mode of operation. So I applied a different differential equation in green, and then in blue I applied a second differential equation. Right now, notice that I'm here computing the reachable set in yellow. So this is mode 1, this is mode 2, this is mode 3, and finally this is in mode 4. Right. So here I'm doing all these aggregation and deaggregation in the background. You cannot even see where exactly I'm doing the aggregation and deaggregation. Right. So in mode 4, we compute the reachable set here, right? And I think our goal is we shouldn't go beyond 0.15 or something like that, right? So this is again another example where you couldn't do it without actually without actually doing the aggregation and deaggregation. So for those who have asked for the tool that we are using, the tool that I'm talking about is this tool called HYLA, which is Hybrid Linear Automata Analyzer. And here is a GitHub repository, and all the code of HYLA with all the branches is available here. So in fact, right now we also have a Docker image. So if you want to do Docker, you can just install it in the Docker. right? I think we also have a pip install in one of the branches that there can be a pip install as well. So yeah. So again, we are actively working on this even now. So no wonder that there are multiple branches of this, right? Okay. Okay. Any questions until now on the deaggregation and aggregation methods? Okay. So what I want to do now is basically go to what is called as extracting count examples. So what I'll do is I'll basically do a short break of 5 minutes just to stretch myself and come back. So I'll resume the yeah, I'll resume the presentation in 5 minutes. So why don't you take a break for 5 minutes? Yeah.
Yes, sir. Yes, sir. Fine. Thank you.
Okay, so let's come back. Um, okay, mm, you can hear me, right?
Yes, sir.
Am I audible?
Yes, sir. Yes,
Okay,
sir.
okay. Um, okay. Oh God, this is again. I don't know what happened. Let me do something that is risky. Let me close this presentation. Let me see. Give me 1 second.
Yes, sir. No problem.
So I'll do one thing. I'll actually drop out if you call and come back. It looks like there is some specific problem with the browser. So I'll just drop out and come back. If that's fine.
Yes, sir. Yes, sir. Fine.
Yeah, am I audible now?
Yes, sir. Yes.
Okay, okay. Mm, okay. Mm, You can see my screen now, right?
Yes, sir. Yes, sir. It is.
Yeah.
Yes.
Yeah, sorry. Yeah, I think I had to restart my computer. Sorry for the problem. So, yeah, so what we'll do is in the last part of this talk, what I want to do is we can do something much more interesting using the tools that I've presented here. One of the things is we can extract several counterexamples. So, whenever one of the first things that you would want to do whenever we talk of models and model checking is suppose I have a hybrid automata as given here, and I want to implement a model checker, which if the safety specification is satisfied, it will give me a safety certificate. In the case of HILA, our safety certificate is the reachable set, and or otherwise you would want to give a specific counter example. So one of the reasons why we adopted the simulation equivalent reachable set is because we can have this specific counter example. Right? Okay. Now here is one of the so if you give this specific filtered oscillator model to SpaceX, it will and if you put the safety constraint as x greater than or equal to 0.5, then SpaceX will return you this is the reachable set, as in the set in the purple is the reachable set. Right? The problem with this is that there is an overlap with the value of x greater than or equal to 0.55 and yeah so in this particular set you can see that yeah so here you can see that there are some aspects of the reachable set that are unsafe, right? But what am I going to do with this description of the unsafe region, right? I want to use some sort of a very specific counterexample so that I can use it in either my control design or refining of my controller. Right? So this entire unsafe set is not very useful for me. Right? Let's go to the other way, which is something similar to falsification. If you don't know what falsification is, don't worry. But suppose that you have some model, right? And the model has some input-output behavior. Right? So the input is some input signal, and based on that, the trajectories are shown in here. Right? So here I give several input examples, and I give you several outputs. Right? If you have, suppose that if you have, so S-Talido is one of the tools that performs falsification, and in this case, I have, suppose I have my initial set as this green set, and I want to falsify or give a specific counterexample that goes to this unsafe set, right? So in this particular case, the Estalero will eventually say that, okay, this trajectory goes through the unsafe set, and this is a specific counterexample. But the problem with falsification methods is that they are the best effort methods. That is, I generate some trajectories, and that's it. I don't know what will come out of. So if I cannot find a specific counterexample, it doesn't mean that the system is safe. It just means that the best effort in trying to find counterexamples just fail. Okay? It's about some randomly generated counterexamples. So we have two very different goals here, right? One is on one hand verification, where you get the complete reachable set. On the other hand, you have falsification, so you'll get some random counterexample. So what we want to do is, from the perspective of control designer, we would want to have some sort of, we would want to give at least an ordering of control, or at least an ordering of counterexamples, and that's what we wanted to do. Right? So here is a very simple example. Right? Suppose I am a control designer and I'm trying to make the tracking error of a specific, suppose I'm tracking a specific quantity. All I want to do is basically make the tracking error close to 0. Right? So now if I have a trajectory, right? Suppose I have a specific trajectory. I can come up with various executions of this specific trajectory, right? So suppose that while doing this tracking control, while developing this tracking controller, I have a threshold that I do not want to cross. Right? Now, the counterexamples that are interesting to me are basically the counterexamples that either have some sort of a maximum threshold or that have a maximum duration of overshoot. So these are some of the interesting trajectories, right? So what we set out to do was to figure out some interesting techniques to give these to generate some of these trajectories which either have a maximum threshold or have a offshoot or have a continuous offshoot duration that is, they stay above a certain threshold. Okay? So we created two different types of counterexamples. We call one as the deepest counterexample and second being the longest counterexample. Okay? In the deepest counterexample, so in the deepest counterexample is the one where you go to maximum threshold, and longest counterexample is the one where you stay in or you violate the threshold for the longest contiguous time. Right? So our goal was to somehow extract these interesting counterexamples from the reachable set computation that we have already performed. And as you can expect, one of the tools that will help us in performing this deepest and longest counterexample is what is called as constraint propagation. So let me explain what is deepest and longest counterexamples. Suppose I have two trajectories starting from x1y1 and x2y2. Right? Now, so these counterexamples go into the unsafe set. Right? Now, if I take the direction x so I have x as the upward direction and y as the horizontal direction. So if I take the direction or the deepest direction that I want to find out as x, the trajectory in the red, which starts from x1, y1, is considered as a deeper counterexample than the trajectory starting from x2, y2. Why? Because in the unsafe set, it goes to a higher value of x. Right? Similarly, if I take y as my direction, the trajectory is in green is the longer or deeper counterexample in the direction of y, primarily because in the unsafe set, it stays or it has the maximum value of y within the unsafe set intersection. So this is how I can rate two different trajectories based on their deepness and deepness as in a specific direction that is given by the designer. Right? So the deepest counterexample is simply the counterexample that is deeper than all the other counterexamples. Right? Similarly, I can think of a longest contiguous counterexample. So observe that here I have three trajectories, blue, red, and green. The green one stays in the counterexample, stays in the unsafe set for the shortest time. The red one stays in somewhat longer time. The blue one comes into the unsafe set, goes out of the unsafe set, becomes safe, and then comes back into the unsafe set, right? So here, although the overall duration or the time instances between the overlap of or the amount of time that the blue trajectory has been in the unsafe set may be potentially longer, but it doesn't have a contiguous unbroken time interval, which is the longest where it has stayed in the unsafe set. If you consider the contiguous presence in the unsafe set, right, then this the time interval from the beginning of the blue trajectory here and exiting of the unsafe set from here, this is the specific this is the contiguous time interval, and then it enters back into the unsafe set and back into the safe zone. This is another contiguous time interval, right? So if you look at contiguous time intervals, red one is the longest counterexample. So what we want to do is extract these counterexamples and give these counterexamples as helpful hints to the control designer to improve their design. Right? Now, let me not go into some of these details. So this is the formal definition of deepest counterexample. The counterexample that has maximum depth. Right? That is, depth of a trajectory is considered as the maximum value of that function transposed with the state, where the state belongs to the trajectory and also in the unsafe set. So I'm not counting all the states, but rather only the states that are in the unsafe set. Okay? Any questions on the deepest and longest counterexamples?
Sir, good afternoon, sir. Sir, what is unsafe state? How will identify that our trajectory is an unsafe state? And one more thing, we are having the verification and falsification. Then how I'll identify that my curve is in verification state or falsification state?
So the unsafe set has to be given by the system designer itself. As in, my job is someone gives me the safety specification, right? So as a verification designer, as someone who is developing verification algorithms, I cannot assume any set to be unsafe set. So it has to be provided to me by the designer. And what often, that answers one part of your question. So the unsafe set completely depends on what the designer gives it to me. And in terms of verification and falsification, both of these techniques are essentially not, these are still in the research phase. These are not actually applied by any of the industry standards. Maybe Toyota is right now doing falsification and getting towards verification, but both of these are essentially two different types of techniques that are applied for checking whether the control systems that they have designed satisfy some of the safety specifications that the control designers put on themselves. So it is not a sequential way, that is, you first do verification and then do falsification. You can do either or, and most of the times people do only one of them. And so what we were thinking of is to combine some of these two techniques together. Does it answer your question?
Yeah, and sir, one more thing, like whether this unsafe state is determined by some parameters or some like linear system equations.
So that's a good question. So there are, the parameters are completely dependent on the specific system of interest, right? So for example, the parameters of unsafe region in the case of adaptive cruise control or control algorithms for vehicles is completely different from the parameters of unsafe set when you're, say, setting your thermostat or maybe regulating temperatures, or that would be completely different from the unsafe specification when you are doing some sort of a chemical plant control, right? So each of these scenarios will demand its own separate unsafe set, and the specification is something that needs to be worked out by the system designer, and only then they can do some sort of verification.
Okay, sir. Thank you so much.
Okay, so so what we did was, using our tool Hyla, we wanted to do some counterexample generation of both of these longest and deepest counterexample. I want to recall from yesterday that the representation that we are using is a star representation, where we have a center and we have two basis vectors v1 and v2, and our set is represented as center plus alpha 1 times basis vector 1 plus alpha 2 times basis vector 2, and so on and so forth, where alphas are all defined by the predicate. So here, if you have v1 and v2 in this way, and alpha 1 is less than or equal to 1, alpha 2 less than or equal to 1, you will have a parallelogram of this specific direction, right? Okay. Similarly, if you have a circular initial set where alpha 1 squared plus alpha 2 squared is less than or equal to 1, your reachable set will be ellipse, but it's just that the change is only in the center and both of these basis vectors, right? Okay. Now, let's go to the how do we construct the deepest counterexample. So we can compute the reachable set at distinct at discrete time instances. So suppose that from S1 we can compute the reachable set S1, S2, S3, S4, and S5. Right? Out of these 5, only S3 and S4 overlap with the unsafe set. Now, what we want to do is the designer has given us the direction in which they want to maximize their depth and find a counterexample. Right? So what we do is we go through all the states that have overlap with the unsafe set and pick the specific point which has the maximum depth in that. So, for example, we do the same. We pick the red point in S3, and we pick the red point in S4, right? And we compare both of these, and out of these two, it turns out that if the depth is given in X, as in here the depth is given in the direction X. So here it turns out that the point in S3 is much worse, or it goes to a higher depth, is a deeper counterexample than the state that goes to S4. Right? So what we do is, once we find out this point can be represented in the predicates and basis of the state S3. Right? Notice that, as I said before, the reachable set only changes by change in the center and the basis vectors, and it doesn't change because of the so the predicate remains unchanged. So if you pick a specific point in the circle, which is alpha 1, alpha 2, the same point, the image of the same point will also be alpha 1, alpha 2, even after some time t. Right? The only change is that alpha 1, alpha 2 is added by some c prime and is multiplied by v1 and v2 instead of v1 prime and v2 prime instead of c, v1 and v2. Right? Now, so suppose now we pick the worst case point in the region S3, and we convert that into the specific valuation of the coefficients in the basis and center of S3. Right? From the reachable set computation, what we know is that this point should have also originated from C0 plus alpha 1 prime V1 plus alpha 2 prime V2, where V1 and V2 are the basis vectors in the state S1. Right? Why? Because whenever the reachable set changes, it's only the center and the basis vectors that change, and the predicate remains the same. So if you take a specific valuation of alpha 1 and alpha 2, its image is completed by changing the center and changing the basis vectors. That's it. Right? So if you pick a point here in alpha 1 prime, alpha 2 prime, the corresponding initial point is also alpha 1 prime, alpha 2 prime. So this point is C0 plus alpha 1 prime V1 plus alpha 2 prime V2. Right? So this is how. So again, if you want to compute the worst case deepest counterexample in the depth of y, we pick 2 points here. One is, so you can see the black point. So here in this particular case, we'll pick the point deepest point in y that has overlap with the unsafe set, and the corresponding trajectory is in the initial state starting in this black point. So based on the different direction of interest, the trajectory that gives you the deepest counterexample changes. Right? Is this part clear? Any questions here?
Yes, sir. It is clear, sir.
Okay. Okay. So the algorithm is given in here. I don't want to go into the details of the algorithm. It's basically what I mentioned before. Right? Now let us go to the longest counterexample. So as we have said before, one of the helpful techniques for us is the constraint propagation method. So what does constraint propagation do? Constraint propagation, so if you take the initial set S1 and suppose you have set S3 which overlaps with the unsafe set U, right? Now we want to extract the part of the region and find its map in the initial set that overlaps with this unsafe set. And the way to compute this is as follows. You convert the unsafe set into the center and basis of S3, right? And so unsafe set, when you convert it into center and basis of set S3, you will have a different predicate, and then you need to add these constraints of P and PU. So P intersection PU, this will be the constraint for the overlap in this region. That is, S3 intersection unsafe set is obtained by C prime, V prime, P intersection PU prime. Right? Now, so when you take this image, so what does this mean? It means that all this image of the reachable set intersect with unsafe set is so all the states that are in the reachable set intersection of the unsafe set, those follow or those arrive from the predicate, or those arrive from the part of the initial set which also satisfies the constraints P intersection PU prime. So the box shown in red here corresponds to the overlap with the unsafe set here. Right? Now, if you add one more region, which is S4, if that also has an overlap with the unsafe set, then you will get a new condition, right? So you'll have P intersection P double prime U, right? And that region is shown in the green here, right? So now, if you look at it from the bigger picture, at time step 3, all the states in the red go to the unsafe set. At time step 4, all the regions in the green go to the unsafe set, right? So clearly these two regions intersect. So if you take a region that is the intersection of these two, which means that this goes to the unsafe set in time 3 and time 4 as well, right? Now, if you take a region that is not in this blue but in this red region, it only means that it is unsafe at time 3 but not at time 4. If you take this small region, it means that it is not unsafe, that it is safe at time 3, but it becomes unsafe at time 3 equals to 4, right? So, how do we use this in generating longest counterexample? What we do is we basically accumulate all such. So, what we do is we first compute the reachable set, right? And for each and every one of these overlaps with the unsafe set, we accumulate all the predicates, right? And now there could be multiple longest counterexamples, but the maximum duration where all of these predicates combined will is still viable, is still feasible. That will give us the longest counterexample, right? Is that part clear?
Yes, sir. Yes, sir. It is clear.
Mm-hmm. Okay. So what we do is we go through all the regions in the unsafe set, right? And we successively compute the conjunction of the longest, or we successfully compute the conjunction of these trajectories, and then yeah, so we compute the successful conjunction of these trajectories, and we get a set like this, right? Okay. So here is one specific example. So in this particular case, harmonic oscillator, so we have a specific dynamics here, and we have an initial set, and we gave a specific unsafe set. And now you can see that in the direction of, so deepest counterexample in y direction is given in the red picture here. Longest counterexample is given as the blue one here. So notice that blue one has unsafe set at 1, 2, 3, 4, 5 time instances, whereas the red one, which is the deepest counterexample in y, is only unsafe at 1, 2, 3, and 4 instances. So that is why, I mean, notice that you can see the difference in these two counterexamples, right? HYLA, on the other hand, returns some counterexample. It doesn't have a specific way to generate any counterexample. And this is one way to improve the quality of counterexample generation from HYLA. So we have applied it to adaptive cruise control benchmark. So in this particular case, we start with a specific initial set, which is shown in the green here, and based on the quality that you want to pick, you will get a different longest counterexample, which is shown in the blue here, and you can get a different deepest counterexample. Deepest counterexample, which is shown in the red part here. If you look at the default counterexample that HYLA gives, then it is the one in the pink one, whereas the more informative counterexample is the one that is extracted using our technique, which is the longest counterexample, which is shown in this particular figure here. Okay, so we have some more experiments, and we showed that this method actually works. But what I want to do now is I want to show you two videos. So these are two different controller implementations, and now I want you to tell me which one of these do you find to be a good controller. So here I do controller 1, or rather I'll do controller left and controller right. Right. So I'll first play the controller left one, so you can see how it works. Right. So here I have a follower car. This is applying some sort of adaptive cruise control mechanism. Right. So the car in front slows down and then speeds up as well. Right. So notice that when it slows down, the vehicle automatically slows down to match its speed, and then go ahead as well. Right? Okay, you have seen that part. Now let's see this. So observe that in both of these scenarios, the behavior of the car in front is exactly the same. It might appear different, but it was programmed to be exactly the same. Right? So we saw two examples, one on the left and one on the right. Which one of the controllers would you prefer to sit in?
I think left one is the better one.
Yeah, why do you say that?
I think it maintains the separation from the front of means the car at the front.
Right? It's not just it maintains separation, but it stayed away from the separation for much longer time. Right? It didn't get close, obviously. That is definitely a good part, but it also did not stay very close to the vehicle in front for a longer time. Right? Yeah. So there is a whenever I show this video, most of the people prefer to sit in the controller on the right, except for some people who want to who are adrenaline junkies. So now again, the same technique which we used as constraint propagation before will help us in finding what is called as a longest counterexample. So the only difference between the longest counterexample that I defined before and longest counterexample now is that here we don't necessarily want all of them to be contiguous, right? So here the counterexample can come and go inside and outside of the controller for a so it can go inside and outside of the controller. All we are trying to do is trying to come up with the total time and maximize the total amount of time that is saved, or total amount of time that some safety condition is violated, right? And the way to one of the issues that we face is the problem that happens is when you perform intersection. So so here is one specific scenario, right? So I start from the initial set S1 and the reachable set is S1 to S7, right? If I take the unsafe set image of S5, right, it corresponds to, so this bottom part is in the unsafe set, so it corresponds to this blue region that is shown here, which corresponds to the S5, right? But the region that is shown in the trapezoidal red region, that is the common set of states that state to be unsafe at time units 3, 4, and 6. Right? Notice that these two do not have any overlap. So unlike previous time where you just generate a bunch of constraints and conjunct them, you may not necessarily get anything, right? And the number of instances where you would have to generate all these constraints and perform a conjunction, that is way too many when you can think of scenarios where the reachable set, when the trajectory can stay in the safe and go outside and then come back in, right? Because of these regions, it is computationally hard, and there is some more complication when we go to hybrid systems. So what we did was we came up with two specific algorithms, which are, one is MILP based and another is SMT based frameworks for performing this constraint propagation. So we showed several, we implemented it on, again, adaptive cruise control example. So here are some of the interesting case studies, right? So we took two different controllers. We took two different controllers, controller 1 and controller 2, and controller 1 has this the smooth behavior that goes from the initial set to the although it starts close to the unsafe set, eventually it goes into the desired set, right? Similarly, controller 2 also even when it starts close to the unsafe set, it goes to the desired set eventually, right? But notice that there are two differences, right? One is the longest unsafe execution is of length 7 in controller 2, whereas it's of length 8 in controller 1, right? So this way, this is one metric for comparing different controllers. The second thing is, whenever I mention safe or unsafe, it can also be extended to other predicates. So for example, I have safe and unsafe zones, but I have undesirable or preferred or desirable zones, right? So I can now order my executions based on how long do they stay in the preferred zones or desirable zones or the undesirable zones, right? So if you take controller 1, it stays in the undesired, the region which is from 2 to 5, that is the undesired execution, undesired region. There, the controller 1 stays in there for 13 time units, whereas controller 2 maximum undesired execution is only for time 11 time units, right? So if you compare that, controller 2 is definitely better than controller 1, right? Again, so again, if you look at depth of the counterexample, that is the value of V. Value of V is clearly higher in this specific case, as in here the velocity V goes to all the way until 12, but here the worst case velocity goes until 10, right? So there are all these interesting case studies where you can where yeah so based on different criteria you can generate these counterexamples, and one way to compare controllers is by using these counterexamples as evidence, right? So we have some more experimental results which I do not want to fully get into, but we can generate more counterexamples both using mixed integer linear programming solvers or SMT solvers. And the time taken for mixed integer linear programming solvers is very, very less compared to time taken for SMT solvers. And we believe this is the case because of two things. One is mixed integer linear programming solvers have been around for a much, much longer time, and SMT solvers are just solving optimization problems using SMT is still in a very nascent stage. So there's a lot of tricks that SMT can adapt from MILP, and hopefully we hope for someday that SMT solvers become as efficient, if not more efficient, than MILP solvers. So okay. So with that, what I want to do is I want to conclude my two-part presentation. What I gave is in yesterday. What I presented was I presented an algorithm for computing the reachable set for an n-dimensional linear system using n+1 simulation, and for that I have presented a data structure called generalized stars. Yesterday I talked about generating new techniques for handling invariance. Today I talked about aggregation and deaggregation scenarios or aggregation and deaggregation mechanisms, why they are important, and showed a bunch of case studies. And finally, I talked about MILP and SMT based counterexample generation techniques. In future, what we want to work on is we want to work on linear systems that are again we want to synthesize linear systems that are both safe and stable. And performing this controller synthesis is very, very difficult. There is also a whole rich theory on optimal control for linear systems, and hopefully we'll be able to merge verification into the optimal control problem, and hopefully we have much more robust, safe, and stable control systems. So with that, I want to conclude this presentation. Here are the list of my collaborators, and if you want to find out more about our tool is called Hyla, and the website is available here. Stanley Bach maintains the website. Some of the demo that I showed and the videos that I showed here are already present in that website. You can also go to Hyla either from my Tar Heel Solver Method /Hyla in GitHub or stanleybach.com/Hyla. Both are fairly frequently maintained. And with that, I want to conclude the presentation. I want to thank you guys for being a nice audience, and yeah, and I'll open the floor for any questions that you have.
So, participants, if you have any question, you can ask. Okay, so I think there is no question. But sir, I want to ask something. This is not part of this lecture, but it is something different. So sir, suppose I want to put a scheduling problem which can be verified by any tool which is used in formal verification. So can we get a counter example means by writing such a predicate which will give you a correct schedule?
Most of the scheduling problems. So the student who has done the counterexample generation, he has also worked on using MILP for generating schedules as well. I think, I mean, in general, mixed integer linear programming, which is what I call MILP, is a very powerful tool. And if you use it correctly, you might be able to generate schedules as well, right? So I think I'm not sure if it is used that widely by real-time systems community because solving an MILP is it's not possible. As in, so if you have to decide whenever your task changes, if you have to solve an MILP to get a schedule, it's infeasible, right? So that's why people want to have a static mechanism for checking scheduling. My hunch is it is indeed possible to do scheduling using these MILPs or constraint-based methods. It is. It may just take a bit longer than what you would actually anticipate. So, if you develop a specialized algorithm for scheduling, that would probably be much more faster.
Okay. Okay, sir. Thank you.
Yeah,
Thank
but if you need any help regarding MILP, or in fact if you are interested in working on scheduling and MILP, feel free to send me an email and I'll CC my student. He'll be happy to help you in that regard. He has some experience in formulating these MILP problems and yeah, he can help you with that as well.
Okay, so sir, actually, I was working on mixed criticality systems scheduling. So
Okay.
in that, first I tried to do it with NUSMB, but I failed. So I turned to the algorithmic part, and I did that in my PhD.
Okay,
So,
interesting.
so
Yeah,
yes, sir, you may continue.
I don't know if NUSMB has been used for specifically for arriving at a scheduling, but most likely I think your best bet would be using something like MILP or SAT or SMT type methods for arriving at a schedule, and maybe that may be a good first cut approach. Yeah.
Okay. So, sir, thank you very much for giving us a very good description on this topic. And from all of us from NIT Jalandhar, we would like to have a lecture here at NIT Jalandhar only, not in virtual mode. So, if
Yeah.
you means if it is possible in future, we may invite you to NIT Jalandhar to have a session from you.
Yeah. I'm happy to visit NIT Jalandhar next time I come to India, whenever that is, because we are all living in the lockdown mode, right? So we hope that things become better, and yeah, I hope to visit NIT Jalandhar in person. Yeah.
So, sir, thank you very much for this session, and thank
Mm-hmm. Yeah. Thanks to all the students for attending. I'm not sure how much the students got out of it, or whether I did a good job or not. Any feedback, either about the overall organization or anything, feel free to share the feedback with me. I'm happy to make some changes, and in future, whenever I give such talks to much broader audience, I'm happy to modify this presentation cater to that specific audience. Okay.
Okay, sir. Thank you, sir. Thank you very much.
Thank you.
Okay, participants, and now we are going to share the feedback link, and it will be available in your chat box. Okay, and tomorrow's section will start at 10 a.m. Okay, and I think Professor Sen Mitra will be available for his valuable talk. So I hope that you will join at 10 minutes before that one. Okay, so I think link will be available, and I think feedback link is also available. You can share your concern or your feedback with that. Okay, thank you. Have a good day.
Is there any feedback link for session 2? Feedback link, please.
Anyone, please send feedback link. Send feedback link.
you.